Today, we have the pleasure of having Professor Sari here with us to give us a talk on gamma ray bursts and the relation to fast transients. So Raim got his undergrad degree at Ben Gurion University, then went on to do his PhD at Hebrew University. He was a professor at Caltech before moving to Hebrew University, where he is right now as a professor. So I was telling you all about this school that many of the instructors in this school went to a few years ago. This is Anna, Jared, me, Itai, who's going to be a lecturer tomorrow. So Raim was one of the original instructors for that school. So a lot of the instructors in this school learned their stuff from Raim. So we get to hear it directly from Raim today. So thank you.
Thank you. So indeed, I started my PhD in '95, which is exactly 30 years ago.
Oh, so yes, the microphone.
You were negative too.
I was negative too.
Good for you. I was lucky to do it at the time that GRBs were just starting to boom. Is it on?
Yes.
Okay. So I'm going to tell you today about, basically, I'll summarize my PhD work more or less, and maybe the early stages of the postdoc. But let's make it interactive. So my name is Sari from the Hebrew University. It's in Jerusalem. A little bit of a troubled place these days. So what do you know about GRBs? Let's write some properties of GRBs in here. Is anyone working on GRBs? Okay. This is 10% of the audience. Okay. So what do you know about them, the rest of you? Gamma ray bursts. So they're made of gamma rays. What does that mean? What energies? So these are bursts of gamma rays. Energies are typically, let's say, 300 keV. They have a spectrum. This is nu, this is F nu. The spectrum is non-thermal. It peaks around this energy. It has a high energy tail that goes very far. We're not sure exactly how far. Let's say this is this 300 keV. What you can see from this spectrum is that they are non-thermal. This slope here is slightly steeper than nu to the -1, which means that nu F nu, which is the energy that is coming in each of these logarithmic decades here, is roughly constant. So the energy doesn't decay very much as you go above this. So let's say nu to the -1.2 or something, typically. It changes, it's not a fixed thing. And there is some power law here, which also changes from one burst to another. This is usually marked as nu to the alpha, nu to the beta. So no, it's non-thermal on both sides of the spectrum. Their duration, anybody knows?
Short, 2 seconds.
Yeah, so there is actually a widespread in duration, extremely wide. So if we do a duration distribution of GRBs, it looks something like this. So this is the time, the duration of the GRB, roughly described as the time where 90% of the energy is coming out. And this is the number of events. The number 2 seconds that Andrea mentioned is here. So actually, there are very few bursts with 2-second duration. Many of them are longer, let's say 30 seconds. Some of them are shorter, 0.1 second. It's all very rough. And these are slightly less common than this, at least in the number of observations. So it's not per unit volume, but flux limited. And now we also know that they are slightly different in their characters. These are slightly harder than this, harder meaning higher energy photons than this. We think these are coming from these collapsars or exploding stars. And this population is maybe coming from the merger of neutron stars. So that's the rough ideas. What else do we know about these GRBs? So this is the distribution of duration of different GRBs. If you look at a single GRB, let's take one of the long ones. So it starts here, it goes to 30 seconds. And in between, if you plot the flux, it changes and different bursts look differently. Some just do this. Many of them do this, where these features can be extremely narrow. In the extreme case, they go to milliseconds, but let's say 0.1 second. Much shorter than the duration of the whole event. Yeah.
Do both populations show that variety?
Yeah, it's harder sometimes to resolve this to so many subpeaks, but
Right,
yes.
'cause it's already so short.
It's already so short, yes. There are some spectral evolution within a peak. It starts harder, becomes softer, and these are all details, but this is the main characteristic here. Okay, what else do you know about GRBs? Yes?
Oh, sorry, I missed it. So what are those two lines in the?
This and that?
Yeah.
Different GRBs.
Oh, I see.
Okay. Yes.
These spikes are generally not periodic.
Yeah,
right? Or
right, no, not periodic. I didn't try to do something periodic. It's very erratic, almost random looking. Some have precursors, maybe some dead time, as long as the burst itself, and maybe these are still somewhat mysterious. And the topic of today was relativistic explosions. So why are these relativistic explosions? How do we know that gamma ray bursts are relativistic explosions? Yeah.
Is it the break,
The break in what?
the light curve?
In the light curve of the afterglows, we'll get to that. This is how we know that they are jetted. But it's also related to the relativistic nature, you're right, yes?
the energy.
The energy, what about the energy? So in order to translate these fluxes to energy, we need to know distances. And for a long time, this was a big puzzle. We didn't know the distance to gamma ray bursts. There was a satellite, it would measure some X-ray or gamma ray photons, but we didn't know the distance from which it comes. We had a rough idea of the direction to within 1 degree. And within 1 degree on the sky, there are so many things, we couldn't find the exact host galaxy, and we couldn't know the redshift. Now, we know to locate them much better and much faster. We can look at the host galaxy. We have this thing called afterglow that helps us. I'll get to that. But we have distances, and the distances are cosmological. There were some hints that the distances are cosmological already before, but now we know this for sure. So you can take this energy that you measure at your detector, multiply by 4 pi the distance square, and you get the energy emitted from the source. And the energies, they vary, but they can be 10 to the 51 ergs, maybe 10 to the 54 ergs. Varies dramatically from one burst to another, but very highly energetic. Why does it mean that they are relativistic?
They are short and non-thermal and energetic.
So
it means that the source needs to be relatively small.
small source, okay.
And
So you can take this time scale, maybe a millisecond, maybe 0.1 second, and maybe put naively an upper limit to the size of the source that emits these things. So this short time scale that goes down to milliseconds point to what? Maybe neutron stars, maybe black holes. Has to be something small, which the crossing time is shorter than this time. Okay, why does it mean that it's relativistic? So we have several clues. The first one we had, I'll tell you in a second, But later on, we got to resolve some of them. And we got to see that at late times, they have this big size, which implies a relativistic motion. So some of it we actually see. We resolve the object and we see that it's moving relativistically. But these are rare cases. But we have a theoretical reason to think they have to be relativistic. And this is because of pair production. Which is related to what Itai was saying. What is pair production? Everybody knows this? No. This is a photon. This is a photon. This is an electron. This is a positron. So two photons come in, they collide, they create an electron and positron, pair production, because you produced a pair of electron-positron. What is the cross-section for this interaction? Huh? Klein-Nishina if you're at high energies. Let's say, okay. Yeah, Klein-Nishina is a good answer, actually. What if I want some numbers, what is it? Which kind of cross-section describe this phenomena? Thomson. What is usually Thomson referred for? It's not usually this. You have an electron, you have a photon. The photon is hitting the electron. You ask what is the cross-section of the electron for scattering. But you can see this is the same diagram. If you switch this, so you have, instead of coming out positron, you have an electron coming in, electron coming out, photon, the reverse of a photon is also a photon, photon coming in, photon coming out. So an electron coming in and out, a photon coming in and out, it's the scattering of a photon by an electron. So it's the same process, just viewed differently. So therefore, the Thomson cross-section is the relevant one. So sigma Thomson. What is sigma Thomson?
10 to the minus 25. 10 to the minus 25.
Yeah, 6 times 10 to the minus 25 centimeters square. It's related to what we call the classical radius of the electron. So it's, what is that? 8/3 pi. The classical radius of the electron square. The classical radius of the electron is the radius an electron needs to have in order for all its rest mass be produced by its charge. So this is the energy of a charge E spread over a distance R, E square over R. And if you want all of that, this is energy, to be the rest mass of the electron, you can ask what is the radius. This is called the classical radius of the electron. So the classical radius of the electron is E square over m electron C square. So this has units of radius. Square it, it's units of area with some pi's. And this is the Thomson cross-section. So this is the cross-section for scattering of light by electron, but this is also the cross-section for pair production. Why do we care about all this? Because we can calculate how many photons this GRB has, because it has 10 to the 50 something ergs, and the energy of one photon what is that? We said 300 keV, maybe an MeV, let's take an MeV. MeV is 1.6 times 10 to the minus 12 ergs. So if I divide, no, this is electron volt. MeV is 10 to the minus 6. So if I divide this number by this number, I get the total number of electrons in my photons in my explosion. So the number of gamma photons in a GRB is something like 10 to the 57. If I took this number, maybe more if I took this number. So lots of photons. So I can calculate the optical depth for this interaction in the explosion. So suppose I'm not even trying to find a mechanism that will produce the gamma ray burst. I'm allowing you to put all the photons already there, all the photons that you see, in some small environment that will give you this short duration. So let me explain this again. So I have a source. This is not even the source. This is the location where the photons are located before they escape. The source has to be small. It has to be smaller than c times delta t. Delta t being this variability time. Let's call it delta t. So this is what, if this is a millisecond, this is 3 times 10 to the 10. So this is like 10 to the 7 centimeters. So that's why we said a neutron star is a good candidate, black hole even better. So the source has to be with a radius smaller than this. And in that radius, we have to stick so many photons. The total energy divided by the energy of the photon, 10 to the 57 photons. Then we can calculate the optical depth. So we already seen in several talks before, the optical depth tau is given by the cross section, which is sigma Thomson, times the density of the photons, which is this 10 to the 57 divided by 10 to the 7 cube. This is the density of the photons, times r. This is a dimensionless quantity. This is dimensionless. This is length, cube, length square. So it's dimensionless. So what do we get from this? It should be some huge number. Let's see. So this is 21, 36. What is it? 11, 18. Dimensionless. What does it mean? If a photon wants to escape out of this, it will hit 10 to the 18 photons before, other photons before it comes out in this cross section. So the photons will interact, just a minute. They will create pairs. The pairs themselves will interact with the other photons. And the whole thing will be thermalized. And I'll get a thermal spectrum.
Even 10 to the 18 squared number of.
Yeah. So this is the paradox. It's called the compactness problem. It seems like we're doing everything that is necessary to get this event. We're limiting the photons to come out of a source that is small. And we see that they can't come out. They must interact with each other. If they would do that, they will never end up with the spectrum. They will have a thermal spectrum. Thermal spectrum is steeper on both sides. It has an exponential decay. And here is nu square, while this is closer to nu to the 0. Okay, so what's the result out of this paradox that we just arrived to? I already said it in the very beginning. This is the motivation to explain this. Relativistic motion. That solves the problem. So I want to show you how it solves the problem. It solves the problem in several ways. One, it eliminates this. I will explain. And the second, Andrea, you had a question you want to what?
I'm not remembering why we care about pair production to begin with in this case.
Because if you have photons, they will pair produce. When they pair produce, it's an interaction that changes the energy of the photons, of the electrons, of everything, and it will thermalize the spectrum.
And we have a non-thermal
And
change.
we have a non-thermal thing.
But
So
obviously, it would be thermalized if something's wrong. Okay, thanks.
yes. So we need, if you want to see a spectrum like this, you need an optically thin source. But the photons themselves make the optical depth. So how can it be optically thin? That is the paradox. Okay? Everybody is clear up to here? Okay. So the way that we clear this paradox is by eliminating this. With relativistic motion, we can have a larger source than this. And also, there is something I did not explain. When you look at this as electron scattering, any photon can do it with any electron. When you look at it in this kind of diagram, 2 photons per produce, you need the photons to have some minimal energy to produce the rest mass of the electrons. So what's the minimal requirement? What kind of energies of photons do I need? What's the rest mass of the electron in units of energy? 0.5 what? MeV, yes. So where is this in this diagram? This is 300 keV. Okay, so we need 500 keV. So maybe I've a little bit exaggerated in here because not all these photons can go through this pair production, but may just I go slightly up and they are in trouble. Okay? But if we use relativistic motion, that makes this trouble even bigger. So let me assume that I actually have a source that is not stationary, but it's spreading with some very relativistic Lorentz factor we'll call gamma. And we'll ask ourselves how large gamma has to be in order to solve this problem of relativistic motion of the high optical depth, this 10 to the 18, and bring it below unity. Okay, so suppose we have a source. I'm making a big circle because it's much bigger than this. It's not limited by this anymore, and it's expanding relativistically to all directions, let's say. Okay, and we are the observers over here. And we ask how big can this be without violating this tiny fluctuations time that we see. Okay, and the trick is, actually there are several tricks and they all give the same answer. I'll go through at least two of them. First, you don't see this whole fireball. Why? Yeah, in relativity we have beaming. So if you have something that emits isotropically in its own local frame, if it's moving, an observer from the outside will see the photons that are emitted isotropically in the frame of the emitter beamed within 1/gamma of the direction of motion. So if you have an isotropic emitter, in its local frame, it emits something like this. Let's say these are the electrons or whatever the emission mechanism, we haven't discussed that yet in this fireball. But this fireball is expanding relativistically. So in the frame of the observer, these photons will look very much beamed. Only a few will go the wrong way. And this opening angle of this cone is 1/gamma. So that means the photons that are emitted from here, when I'm the observer in here, I'm not going to see them because all of them are going to be directed this way. So I don't need to care about this side of the fireball. That's why I don't care about this R/C that I was caring about before. So what part should I care? What about this one over here? Do I see it? No, that emits up. What about this one? Maybe, depends how big gamma is. If gamma is 100, I don't see that one either. So what I see is a small cone of opening angle 1/gamma, where the emission from the side of it are directed within 1/gamma from the direction of motion, and that one just hits me. Okay? So the opening angle, the fraction of the whole sphere that I see is 1/gamma. So how does this relate to this? If I'm saying that all these photons were emitted simultaneously at some time, why would I have any delay between two photons? What was the old argument here? There is a photon here and there is a photon here. And the traveling time between them is 2R/c. So 2R/c has to be smaller than delta t. What will be the same argument here? I have this photon, which is the closest to me, and this photon, which is just slightly behind. So let's make an enlargement of this here. This is the part of the sphere. This is the edge of what I can see, 1/gamma. And this photon is slightly farther from me than the photon on the line of sight. What is the distance between them? One is at radius r, and the other one is at radius also r, projected to this distance is r cosine 1 over gamma. So it's r times 1 minus cosine 1 over gamma, but 1 over gamma is small. So cosine of a small angle is 1 minus the angle square divided by 2. So I get r over 2 gamma squared. So now it's not that r over c has to be smaller than delta t, like before, but this has to be smaller than delta t. This divided by c has to be smaller than delta t. So it means that the radius can be much larger than what I had before. So if I plug this to the same calculation for tau, I get that tau is the same 10 to the 18 I had before. Now let's see, what did I gain? I gained a larger radius. And what power of the radius is coming in here? So there are 3 in here and 1 in here, so 2 on the bottom. And each radius has 2 powers of gamma. So now the constraint is r has to be smaller than 2 gamma squared c delta t. Before I only had the c delta t. Now I have an extra gamma square, which comes here square of that, so that's gamma to the minus 4. Now there is another thing on top of it. I will not get to the details of it because I want to run forward. But if the source is moving relativistically, the photons in the source frame, they are not 300 keV photons. They are 300 keV divided by gamma. And if gamma is large, they cannot pair produce. So I'll have to go farther up in the spectrum to find these photons that can pair produce. And there are a smaller number of them. So that also helps reduce the opacity. That gives another 2 powers of gamma, depending exactly on what is the slope of this spectrum. So maybe 2, maybe slightly more. 2 is for nu to the minus 1. So this is from the larger radius. And this is from the spectrum. Are you following me? Questions? Okay, so together maybe 6 powers of gamma. And my goal is to get this below unity. So what does gamma have to be?
Three.
10 to the 3 or more. So I apparently took some extreme numbers in here because I used the millisecond. For this, I used millisecond variability timescale, which is not, we don't see in all bursts. If I would use a bigger number here, this 10 to the 18 would be smaller, and this 10 to the 3 will be less of a constraint. But typical constraint for GRBs that we have enough information is 100. So this is why gamma ray bursts have to be relativistic. Yes?
Why is it -2 from the spectrum again?
I didn't really say, but I'll just give you the idea. The photons that we see are 300 keV. We calculated them, the number of them to be around 10 to the 57 photons. This is the number of photons in the peak. In the local frame of the explosion that is expanding.
Is it truly into peak? I thought that the energy was integrated over the entire duration, like the 10 to the 51, 10 to
Yes.
the 54 Earths are like the total.
Yes.
Is the total energy, and like we compute it from the total energy, so it's like the total number of photons is like without the
Yes.
okay, continue, sorry.
Okay. So the total number of photons is 10 to the 57. The energy of each photon that we see is 300 keV. But in the frame of the emitting source, they're not 300 keV. They're much smaller by a factor of gamma. And smaller photons, smaller energy photons than 300 keV, they cannot pair produce because their energy has to be above the rest mass of the electron. So if this is not 300, this is 300 divided by gamma, you have to go a factor of gamma up in here. And only those photons can pair produce. And the number of those is much smaller. That's the extra factor of 2
Oh,
that
I
is coming
see.
in here, because you have to go farther in the spectrum to. If this was a bit confusing to move to the frame of the source, you can also think of, I'll leave it, it's good enough. Okay, so gamma has to be big, maybe 100, maybe 1,000, but you need relativistic motion for these GRBs. Okay. Oh, I said I will give you several reasons why the radius can be bigger. So I gave you this delay between the photon that is emitted on the line of sight to the highest photon that you can see. I'll give you another explanation, which is only looking at the line of sight. And suppose that, I'll erase this. And suppose that as the source is expanding, it starts to emit photons at some radius and finishes the emission at, let's say, twice this radius, because it's unlikely that all the photons are emitted simultaneously at the same time, right? So let's say that I have a relativistic explosion here. And when the expanding stuff arrives to this radius, which we call R, and continues for another R, this is the duration from here to here over which the photons have been emitted. So they have been emitted over a long duration, R. How long of a signal will we see from that? Just from the photons that are on the line of sight. So let's say the first photon was emitted in here. The last photon was emitted in here. At the time that this last photon was emitted, here it is. This first photon, which was emitted here, where is it now? It ran forward. It goes at the speed of light. So it goes faster than whatever is expanding, but not by much. Why? Because the other thing is also expanding relativistically. So this photon is just a little bit ahead. Let's do this little bit like this. And now these two photons are going together to the observer. So the delay time I will see between them is just this. Not the whole R. So how do I calculate how much is this? How long did it take this expanding stuff to move from here to here, if it moves the distance R? Almost C. If I will do C, then they will be at the same place. Right? So this expanding thing moved at some velocity which is almost the speed of light. So it moved at R over V. This is the time that this thing expanded.
The emitting source. The emitting source.
The emitting source moved, and the photon during that time moved R over C. No, at this time, the photon moved that much. So this is the time times the speed of light. This is how much the photon moved. So if I'm doing this minus R, this is how much the photon moved. The emitting source moved R by definition, and the difference between them is what we're after. So what is this? It's R times C over V minus 1, which if you replace the C over V by beta and you remember that the Lorentz factor is this, you get that this is roughly R over 2 gamma squared. So this is the distance between them, and this divided by C has to be smaller than delta T, and we get exactly the same answer that we had before. So both reasoning, the extent by which you see stuff laterally in angles, and the translation of this source that is running after it's photons that is emitting that is shortening the duration that photons will arrive at the observer, they both allow you to have a scale which is gamma square bigger than what you seem to have in your detector. So notice that we haven't done in this calculation any relativistic transformation. This is Newtonian physics. We just use the fact that the photon and the emitter are moving almost at the same speed. It's a Newtonian effect. So, so I want to stress, it will be useful for the radiation calculations that I'm going to do in a second, that you can think of 3 timescales in this problem. So observer, so this will be arrival time. Arrival is 1 hour or 2 hours? Tell me, 1 hour? 2 hours, arrival time. So this is what you will detect. What is the time at which the photons arrive at the observer? You can ask what is the lab frame time of emission. And what is the source frame time? We will care about all these 3. So suppose that the observer sees some time t, meaning the first photon and the last photon have lagged each other by a time t. How much they could have lagged each other in the time that they were emitted, it's t times gamma squared. So this is the calculation we have just done before. This is this gamma square that I just deleted. So let me explain this again. This is if you have a source that is moving that way, almost at the speed of light. It's emitting a first photon in here. This first photon is now here. And the last photon, so I'm calculating this time, the time between the first emission and the last emission, and this small quantity, which will be translated in my detector to the arrival time. So this is smaller than this by a factor of gamma squared. That's what we calculated before. So these 2 photons that I see that created the first and the last photon of my GRB, let's say a few seconds apart in my detector, they were a few seconds times 10 to the 6 apart in their emission time. So they were emitted over a day, but I see them within a second. Okay, because the source is chasing the photons that it emits. I can ask, okay, so the emission took a day. How long did it take in the source frame? That is now a relativistic transformation. And this is this time divided by gamma. So it's gamma times t. So from here to here, it's not a relativistic effect. It's just the fact that the wave that we're following, photons, is moving at almost the same speed as the source that emits them. It's like a Doppler effect, which doesn't have to be relativistic. From here to here, that's a relativistic transformation. Got it? Yes.
So the source frame time would be if I was riding on that circle.
If you were, yeah, moving
little
with the
dot.
emitter, with this white dot, you were riding on it, and you clock the time, you set your clock when you emitted the first photon, you go there, and you stop it when you emitted the last photon.
And that's just the Lorentz.
That's a Lorentz transformation between here and here. If something really took this time in the lab frame, and you ask how much time evolved in the moving object frame, it's shorter by a factor of gamma. Clear? Okay. So this will be important, for example, if I will follow electrons that are moving in that source frame, and I'll ask how long do they have to cool, I will have to take this time into consideration because this is how long they have in their local frame. Okay. How am I doing in time? Oh, very bad. Okay. So, emission mechanism. The first thing that comes into mind when you're talking about this relativistic stuff and things with very low density, we must have low density of whatever, because if we'll have too much stuff, we'll have opacity problems again. We need everything to be optically thin. We need very low densities. And we need this non-thermal spectrum. And the main emission that is relevant for this is synchrotron emission. Everybody knows synchrotron emission? Is that a yes or a no? Sounds like a no. And yeah, yes, I can. That's my purpose here. So you have an electron moving in a magnetic field. Basically, that will emit synchronous radiation if what? If the electron is relativistic. Yes. So you have a magnetic field, let's say this X here, and you have an electron moving in this magnetic field. It's an accelerating electron. Accelerating electron emits radiation. So let's see. What is the force that is acting on an electron moving with some velocity v in a magnetic field? Called the Lorentz force, right? What is it? E, the charge of the electron, V, B, yeah, that's it. There are no more things, so you just multiply all of them. Yeah, and we need a cross, but if it's oriented correctly, you don't need it. And whoever wrote this is using what kind of unit system? This, written this way, it's MKS. In CGS, electric field and magnetic field have the same units, so we can't have this velocity here, we need V over C. This is CGS, and we're in Astro, we do CGS, so this is our equation. And this force is the centripetal force of the electron, so it's the mass of the electron times its velocity square over its radius. So this is my way to calculate what is the radius of motion of the electron. So what comes to be that radius? 1v cancels, m electron, v over EB, C. Where is the C? On top. And if I want to know the frequency at which it rotates, omega, which is V over R, so the V cancels out, and I get EB over m electron C. This frequency is known as the cyclotron frequency. Why? Because it's non-relativistic. So this is the cyclotron frequency. And we'll have to tell you in a second what is the synchrotron frequency. What do I have to do if I want to change this? Okay, before I move to relativistic, I have an electron orbiting in this way, in this frequency. Notice that this frequency depends only on the magnetic field, not on the velocity of the electron. The radius depends on the velocity of the electron, the frequency does not. So if you throw a bunch of electrons, the slow ones will do a small circle, the fast ones will do a big circle, but they will do it simultaneously. And they are sort of synchronized. And people use it when they are doing machinery that accelerates the electron. They're using this fact. But when the electrons become relativistic, this something here has to change. Actually, the only thing that has to change is that because electromagnetism is already relativistic, the mass of the electron is bigger by a factor of gamma. So we get that the radius has this gamma here. And actually this will get a gamma. So actually, as the electrons are becoming more and more relativistic, they are becoming heavier, actually doing the rotation in the same magnetic field slower because they are heavier. What is the frequency that you do see? It's not that. So that's another curious thing. If you have an electron doing this, and let's say that the observer is always to the right here, you can think of the emission of this electron also as beamed to within the direction of motion of the electron. So as the electron is doing this circle, when it's moving this way, it's emitting mostly downwards. When it's moving this way, it's emitting here. And it's only when it's moving at the top of this circle that it emits towards this observer. What fraction of the circle? 1 over gamma. It's always the answer to any angular question. It's 1 over gamma. Okay? So that means that if I will plot for you the electric field that this observer sees, E as a function of time, then I have a periodic phenomena. It's periodic on this time scale, or the inverse of this time scale. This is a frequency, which is long. It's becoming longer and longer as gamma is getting higher. But I see only a fraction of it. So I see a very sharp peak and a very long decay, and then another one. So this is like the electric field. And therefore, the frequency that I will actually see as what we call synchrotron radiation has this duration. And therefore, the frequency is 1 over this. And my question is, what is this compared to this? So this is the periodicity of the orbit of the electron, which we calculated in here. It's long. The gamma is against us, makes it longer. What is the fraction of this out of this? I'm trying to tempt you to say the wrong answer, but I want you to go there. What is this as a fraction of this? Do we have the answer on the board? 1 over gamma is the tempting answer. It's part of the answer, but it's not the whole answer. So the reason is the same thing we had between those two things. So it's true that the emission that we see at the peak here is coming from this motion. But as the electron, sort of very heuristically, is emitting, starting to emit in here and finish to emit in here, it is chasing the photon that it is emitting. So the signal is shorter by this factor of gamma squared. So this is therefore shorter than this by gamma cubed. So if this is the inverse of this, what is this? It's actually for 2 pi gamma m electron over EB. This one, delta T, is T over gamma cubed. Got it? You got the 3 powers of gamma? One from the fact that it's actually a small fraction of the circle, 1 over gamma. And within that small fraction, it's actually chasing the photon that it emits, shortening the duration by gamma squared, like we discussed a minute ago. So therefore, the frequency of the photons, of the synchrotron photons, is higher than this by gamma cubed, which gives us EB over m electron C times gamma cubed, gamma squared. So this is the typical frequency of synchrotron radiation. Got it?
Wait, I'm a little confused.
Yeah.
Why
Tell
do
me.
you get gamma squared instead of gamma? Because this is still the observer frame, so there's still like a time dilation effect.
Why I get this gamma square?
Yeah,
Yeah.
instead of gamma.
I'm doing everything in the lab frame.
Okay.
Okay, so the electron, this motion of the electron, the duration of it, we calculated in here.
Great.
That's in the lab frame, not in the electron frame.
Yeah. So this is the lab frame, still not the observer frame.
Right. And the time over which the electron emits, which is 1 over gamma, all in the lab frame. And now the electron is chasing the electric field that it's emitting. That shortens by a gamma square. So these are 3 powers of gamma. So that gives us this m electron over EB gamma square. Okay. I'm missing some C here, right? Doesn't matter. How much energy is emitted by this synchrotron emission? We can use the relativistic equivalent of the Larmor formula. We have an accelerating electron, but I'll give you a heuristic way to do it. Okay, let's do the following thing. I don't have a tennis ball, but I have this chalk, and I have my arm. My arm is moving at some velocity v. It hits that chalk. What is the velocity of the chalk compared to the velocity of my arm? So I have a stationary chalk. I'm moving the arm. I hit the chalk is moving. What is the velocity of the shock compared to the velocity of my arm? My arm has velocity v. What's the velocity of the chalk? Ratio of the masses, I'm a big guy. The chalk is a small guy. Ratio of masses is very large. My hand doesn't feel that the chalk is there. 2v. Yeah, how do you prove it? Fantastic. You move to the reference frame of the arm. What do you see? You see the chalk is coming in at velocity v. It's reflecting at velocity v. Now you move back to the frame of the lab. V plus v, 2v. Okay? Now I want to do the same thing relativistically. So I have the chalk. I'm moving my arm relativistically with a Lorentz factor gamma. It hits the chalk. What kind of Lorentz factor will the chalk have? So let's follow her logic. We'll move to the rest frame of the arm. What do we see? We see the chalk coming in. At what Lorentz factor? Gamma. It hits my arm, it's reflected with a Lorentz factor gamma. And now I do a relativistic transformation, gamma, on something that is already moving at gamma. What does that come to be? Gamma squared. Okay, so the analog of this 2v in the non-relativistic case is a gamma square in the relativistic case. So let's say there is a photon standing here, and the relativistic electron is coming and scattering it. What kind of energy will that photon get? Gamma square times its original energy. It's being boosted by gamma square. So I will use this to say that the power of synchrotron is the following. So the heuristic thing I'm saying is the following. I have magnetic field with some density. You can think of this as virtual photons hanging around in the room. And then I have an electron that is coming and scattering that energy. It does that with the cross-section sigma Thomson, more or less. Actually, exactly. It moves at the speed of light. So this is the volume per unit time that this electron is scattering. Right? So it moves with a cross-section sigma Thomson at a velocity c. So per unit time, this is the volume that it scatters. The magnetic field energy density is what? b squared over 8 pi. So this is the volume per unit time times the energy density. It gives me energy per unit time located in the scattering region of the electron. And each scattering boosts the local energy by gamma squared. So this is the synchrotron power. There's a factor of 4/3 here. Where is the factor of 4/3 coming from? It's a combination of two things. Actually, when you do Lorentz transformation of gamma plus gamma, it doesn't come to be gamma squared, it's 2 gamma squared. So I should have had a 2 in here. And not all the photons that are hitting the electrons are hitting it perpendicularly. Some are coming this way, so they are scattered less favorably, so that reduces this 2 to 4/3, but it's not important. Okay, so this is a synchrotron radiation. We know the power, we know the frequency. We can talk about the spectrum around that frequency. It's too complicated, so I won't go into this. But the spectrum looks like this, nu to the 1/3, and then exponential cutoff. This is the frequency, nu synchrotron or omega synchrotron, which is this EB over m electron c times gamma squared. And the power here depends what you plot in here. If I said this is nu to the 1/3, then I plotted F nu, which is energy per unit time per unit frequency. So it's actually this divided by this, because it's energy per frequency. This divided by this. So the peak here is proportional to, you see the gamma square cancels. B, I have 1 power. Yeah, so it's proportional to B and physical constants. Okay. Now, the thought is that there is some shock wave. Here's Elena. Elena, you want to come in? Later. Elena was also doing her PhD at the time that this whole thing was booming, and she was working on these structured jets, which are becoming more relevant now, and I'll tell you this if I have time at the end. Okay, so where are we? We had, we were thinking that some shocks are involved, but because of my short time in here, maybe I will jump to what do we think is happening later after the gamma ray burst event. But what I'm saying about synchrotron radiation is probably also relevant to the prompt emission itself. But I will talk about this fancy thing called afterglow that follows right after gamma ray burst. So I don't know, people who follow GRBs, we have this flash of gamma rays lasting a fraction of a second or a few seconds. After that, there is still an emission in all wavelengths, actually starting from radio to X-ray and gamma rays, lasting a long time, sometimes years after the event. Anna, what is the record? How long have we seen afterglow? 5 years?
8 years, sounds right.
Yeah. Yeah. So usually in the radio, you can follow them for a long time. So the picture here is somewhat similar to the supernova picture, but a relativistic version of that. But actually in the supernova, I think nobody actually mentioned this part of the supernova remnant, the part of the supernova that comes years, many years after the explosion. So I think Brian mentioned, okay, I'm gonna erase this. Brian mentioned the interaction of the ejector with the surrounding, but he talked about only the very early stages. He talked about, I think he said the flux is constant, because he said he has an ejector moving with a constant velocity, interacting with material who has a density that is decreasing like r to the -2, and the decrease of the area and the decrease of the density gives a constant flux. But this notion that the material is moving at a constant velocity cannot last forever, right? How long can it last? Until it sweeps up its own mass. So let's do non-relativistic explosions. And then we'll do the relativistic version of it. So after I already swept up my own mass, I must have slowed down. I cannot have an ejector that will collect more than its own mass and will continue to move at the same velocity. I will not conserve energy this way. So my initial energy, which was the kinetic energy of the ejector. So in supernova, what is this number? 10 to the 51. Yeah, not the 10 to the 49 that we see in photons, not to the 10 to the 53 that gets lost in neutrinos. This 10 to the 51 that is coming out as mechanical energy in the ejector. This is now reconverted back to a combination of thermal and kinetic energy as it sweeps up the surrounding medium. So if the surrounding medium has a density rho, and the ejector already swept up a distance r, so this is how much mass the ejector collected. And that mass is moving with some velocity v, which I will call r over t. And therefore I have this equality. Equality is a big word for this, but this tridality. And that gives me that the radius goes like E over rho to the 1/5 times T to the 2/5. This is the famous set of Taylor scaling for an explosion, hitting the surrounding and decelerating as you go. So the velocity, which is r dot, goes like T to the -3/5. So that's the non-relativistic stuff that comes once you have collected your own mass. And in supernova, it starts thousands of years after the event. What's the relativistic equivalent of this? Help me out. I want to write this equation. So I have an ejector that has total energy of E. So E is going to stay the same E. It already passed some radius R in a density rho of the environment. So how much mass it has collected? Don't be shy. It's the same. It's all cube. But now I don't multiply by v squared because I'm talking about relativistic stuff. So what should I do? Gamma squared. Y squared. That's the right answer. But y squared. If you have a mass moving relativistically with a Lorentz factor gamma, what is the energy of that mass? Mass m moving with a Lorentz factor gamma, the energy is gamma m. But the right answer is gamma squared, y squared.
I just said that because it's B squared.
Yes, but as the non-relativistic, I understood that. As the non-relativistic equation for kinetic energy is half mv squared, the relativistic version is gamma mc squared. Where if you take gamma to be 1 over square root of 1 minus beta squared, mc squared, and if you assume beta is small to get the non-relativistic limit, you get 1 minus half beta squared times mc squared. So 1 times mc squared is mc squared, and beta squared times c squared is v squared. This is plus. You get plus half mv squared. So this is the non-relativistic kinetic energy part, which we're all familiar with. But in the relativistic case, there is only one power of gamma, not gamma squared. So why is the correct answer gamma squared? There are two ways to think about it. One is the chalk example that we had. So if you think of the surrounding material as these particles, when this ejecta hits them and the ejecta comes with a Lorentz factor gamma, what do they get? Gamma squared. That's why each one of these rho r cube mass is not moving at gamma, it's moving at gamma squared. Another way to look at it, which is slightly better, I would say, is the following. So as it's a shock wave moving into the ejecta, it pushes the ejecta with a Lorentz factor gamma, but the particles inside also have a thermal Lorentz factor gamma. So even in the rest frame of the moving ejecta, they have a higher rest mass because of their thermal energy. So one gamma, if you want to think of it like this, in the rest frame of the shocked material, this is the energy of the shocked material. Each particle there has a Lorentz factor, a thermal Lorentz factor gamma. And the whole thing moves at a Lorentz factor gamma. Yes?
So why does a thermal Lorentz factor and a bulk Lorentz factor have to be?
Why are they the same? You can use this chalk analogy that I gave. You understand that each particle must have a gamma square. You can think of the following. You have a shock wave. The shock wave is moving with Lorentz factor gamma. The fluid behind the shock wave is moving slightly slower than that, with a Lorentz factor that is smaller by square root of 2 out of this gamma. This is the Hugoniot conditions that I won't have time to talk about. Let's call this little gamma, which is gamma over square root of 2. Look at everything from the point of view of this material, of the shocked material. What do you see? You see these particles that were at rest in the lab moving towards this material with a Lorentz factor little gamma. They come in, the shock wave is propagating towards them, they come in and they join a small layer behind the shock that is now thermalized. But you can do the conservation of energy particle by particle. So that particle had a Lorentz factor gamma, and now it's at rest. So to conserve its energy, its thermal motion has to be gamma in this frame. And this is the frame of the local fluid, so that's its thermal motion. So the exact thing, if you want, it's really this. It's the gamma of the fluid motion that is the thermal Lorentz factor, not the gamma of the shock. Okay. Yes.
Sorry, I know you've said this twice already, but
Yeah.
can you explain again why the chalk analogy gives us the gamma squared?
Yes. So I have this ejecta, and it hits the surrounding. Think of the surrounding as particle by particle. Just let's look at one. There is the ejecta coming at the velocity gamma, Lorentz factor gamma. It hits a particle, that particle gets gamma square. That gamma square, you understand? No.
Can you explain that one again?
Yes. So we move to the frame of the ejecta. We see the particle coming towards the ejecta with a Lorentz factor gamma, reflected by a Lorentz factor gamma, and the Lorentz transformation of gamma by a Lorentz boost of gamma gives gamma square,
Okay,
or actually 2 gamma
That's right.
square.
Okay, perfect.
Okay. Okay, so this is the right thing. So now I can, this gives me gamma as a function of R. Let's say in a constant density environment, gamma goes like R to the what? Minus 3/2. Yes? But I want everything as time, as a function of time. Which time?
Observer time.
The arrival time of the photons. Not R over C, but R over, it's written in here, it's R over gamma square C. So actually, I want to replace R by gamma square, the time at the observer, to the minus 3/2. So now I have to solve this. This is the same gamma. I want to solve this for gamma as a function of time. Help me out. This is minus 3. So I bring it here, it's 4. t to the -3/2. So I have gamma t to the -3/8. Yes, I think that's right. So this is how the Lorentz factor decreases as a function of time, but not the real time, the time of the arrival of the photons, which is contracted compared to the real time by a factor of gamma squared. So as function of the real time, it's like this, because r and t are proportional to each other. The thing is moving relativistically at the speed of light almost. So this r is almost t, but not the observer time. It's not a Lorentz transformation, it's just a Newtonian thing following the photons that you emit. Okay, so we have it. This is the equivalent of this. This is the equivalent of this, and so on. Okay, so now I want to use this kind of scaling. Actually, if you use this formula, you can track back at what time you started this deceleration. Because this just gives you a power law. You can collect the coefficients in here. I won't do it, but I'm just telling you a curious thing. If you plot gamma as a function of time, we've seen this, you can find out when was it equal to the original Lorentz factor, and you can ask yourself how much mass you have collected here. So what is the mass that you had to collide with in order to start decelerating? Anybody wants to guess the answer? Andrea had the answer for the non-relativistic case. What was it?
You have to sweep up your own mass.
Your own mass. What's the answer in the relativistic case? Yeah, m over gamma. You have to collide even with a smaller fraction of your own mass. And your own mass is already small because you're moving relativistically. So for the amount of energy you have very little mass.
Is that because the mass is gamma times the rest mass?
The effective mass, yeah, it's this gamma, this extra gamma that we have here that comes there. Okay, but let's leave that. So now let's try to understand what will be the synchrotron radiation coming out of such a relativistic explosion that evolves according to these scalings. So let me do this here. So now the game is as follows. Okay, I'm going to do that in 2 stages. Stage 1, I'm not talking about an explosion. I'm just talking about relativistic electrons in a magnetic field, but I won't have just a single electron, but I'll have a collection of electrons whose energy distribution is a power law. And I will ask, what is the synchrotron spectrum of this? It's just a combination of the synchrotron spectrum that we discussed before, where we'll have some sophisticated parts of it. So here's the model, magnetic field. Just a number, I won't care what it is for now, plus power law distribution of electrons. Gamma, Lorentz factor, BND gamma, gamma mean, and the power law, gamma to the minus p. Got it? So this is my model. I have magnetic field, and I have a power law distribution of Lorentz factor starting from some minimum. Whether this is the reality or not, I think it's somewhat of a hard question. People think that because the shock is relativistic, most of the electrons behind the shock are accelerated to this power law distribution. This p is thought to be around 2.2. This is coming both from some theoretical grounds and from observations.
Is this the Fermi acceleration?
Yeah, Fermi acceleration in these shocks, relativistic shocks. Okay, so we saw already what is the synchrotron spectrum from a single electron. Now all we have to do is combine a bunch of electrons. So when I'm saying that this is the spectrum of electrons, what do I mean? I mean that the shock itself accelerates the electron to this spectrum. Whether it stays this spectrum or not, we will discuss it in a second. Okay, so we wrote the synchrotron equations. They were the power of synchrotron is sigma Thomson C V square over 8 pi times gamma electron square. And the frequency, nu synchrotron or mega synchrotron, was EB over m electron C. This is the cyclotron frequency. And then when we do it relativistically, we get 1 factor of gamma here and 3 factors gamma upstairs, we get gamma electron square. Okay, so now I want to use this over this parallel distribution of electrons. So I do it one by one. I take this gamma min, let's call this gamma min just gamma m, so I don't have to write all this long word. Gamma m has some corresponding frequency from this formula. So these electrons, which are the majority of the electrons, they emit this nu to the 1/3 low frequency spectrum that I discussed and did not explain, and an exponential cutoff. These electrons farther up, they also do the same. They have this nu to the 1/3 and an exponential cutoff, and so on. But there is a minimum here. So this is the lowest energy electron. This is a higher energy electron, and an even higher one. And the combination of this gives me some power law that is related to this P. So this power law comes to be nu to the minus P minus 1 divided by 2. How do I know this? I can estimate how many electrons are within a Lorentz factor of about gamma. Well, I wrote it here. The ND gamma goes like gamma to the minus P. So if I want the number of electrons, not per unit Lorentz factor, but around this Lorentz factor, I have to multiply this by gamma. So I get that the number of electrons is gamma to the minus P plus 1. Each one of them is emitting this kind of energy. So it goes like gamma squared. And that energy is distributed over a frequency, which is also gamma squared. So this is F nu. And this is proportional to gamma to the minus P plus 1. But nu and gamma are related this way. So therefore it's nu to the minus P plus 1 over 2, or whatever I want to say. So far simple. Now I have to do 2 corrections at the higher end and at the lower end. There seems to be some paradox again here. As you go to higher and higher Lorentz factor of electrons, their power, the power they emit, is increasing as their Lorentz factor square. But the energy they have, the energy, what is the energy of electron with a Lorentz factor gamma? Gamma, so only 1 power. So eventually, as you go far enough to high Lorentz factor, they emit presumably more than they have, because their power is increasing more than their energy. So at some point, this thing would break. And the break here is because the electrons actually cool. They start emitting at this rate, and then they lose their energy, they cool down. So if this is the injected power of electrons, the lower ones they can emit for the whole lifetime of the system, but the higher ones maybe not, and they cool before over the life of the system. This comes to be nu to the minus P over 2. There are several ways to see it. So this slope is different from that slope by 1/2. where is this 1/2 coming from? You can calculate how long the electron can live. It's given by its energy divided by its power. So it goes like 1 over gamma. And 1 over gamma is 1 over square root of nu, which is this difference. So they live shorter and shorter as you go to higher in frequency by nu to the 1/2. So that's one way to think about it. Another way to think about it is to say, well, these electrons have cooled. It means they emitted all their energy. So you just take their energy. So this is the number of electrons. Their energy is 1 power of gamma, and you divide that by the frequency. So you just say, these electrons have given all their energy. That gives immediately this. At lower frequencies, yeah, I'm in log scale, so I can go to negative numbers. What happens at lower frequencies? Anyone doing radio observations should know. Can I have nu to the 1/3 continue forever? Self-absorption, exactly. What is the spectrum of synchrotron self-absorption? 5/2. This is what you will see in every textbook, but in this class it's going to be 2. That depends on the situation. So if the, okay, I will explain. So this frequency we call nu-m, because it's the nu of the electron with gamma m, the minimal Lorentz factor. This frequency we call nu-c, which is the cooling frequency. So this is the frequency that is emitted by synchrotron of electrons that can just cool over the edge of the system. And this one we call nu-a for absorption. So in this order, if nu-a is smaller than nu-m, that is smaller than nu-c, the spectrum is as I plotted in here. In many radio cases, nu-m is smaller than nu-a, not in GRBs, but in other galactic synchrotron sources. And then it's the 5/2. Okay, so I think I explained how to calculate nu-c, did I? You have to look at the power that is emitted by the electron. So if this is the power, you write sigma Thomson c b square over 8 pi times gamma c square. Gamma c is the Lorentz factor of the electron that is emitting the cooling frequency. This is the power times the age of the system. If this is equal to the energy of the electron, gamma c m electron c square, this defines gamma c. And from gamma c, you can substitute in here and calculate nu-c. How do I do this? What's happening in here? Where is this nu square coming from? Have you seen nu square before in F nu?
Rayleigh genes.
Exactly. It's the low energy tail of a thermal spectrum. And the source, a thermal source, or a source that has a random motion of the electrons, cannot emit above this thermal limit. It will start absorbing the same rate that it emits. It becomes optically thick to its own radiation at these frequencies. So actually, all I have to do, if I want to calculate nu-a, I can say, okay, I already calculate the maximum in here. Let's call it F max. The low frequency part of that is nu over nu max to the 1/3. This is the synchrotron emission of optically thick synchrotron emission. When this is equal to the Rayleigh jeans low energy tail of electrons with this Lorentz factor, you'll have self-absorption. So what is that? What's the Rayleigh jeans thing? It's 2 nu square over c square times kT times the size of the emitting region. What's the kT? It's the effective temperature. This is not really a thermal distribution of electrons, so there's no really a kT. but I have a Lorentz factor gamma m, and I can say that this is gamma m electron c squared. So I can use that to calculate nu A. So from this, I'll calculate gamma c. From this, I'll calculate nu A. I won't do it because we're out of time. Okay? Is this clear? Now, is that a yes or no? Is it clear, or do you want me to repeat anything in here? Suspicious.
You don't have sufficient time for you to repeat the last like 8 minutes.
What are we doing with time? How are we in time?
You
It's
have
10:24.
5.
10:24. Okay. So the idea here is that then we will follow these relativistic scalings. We'll need to write some prescription of what is the magnetic field doing as a function of time. We'll need to have some prescription of what is the minimal Lorentz factor of the electron, what is this doing as a function of time, and then plug it into those ideas and understand how this broken parallel spectrum evolves in time. So I will give you just the ideas. So for the magnetic field, let's start with the electrons. Each proton behind this shock wave has a Lorentz factor roughly comparable to the Lorentz factor of the shock. We discussed that already. The thermal motion is about the Lorentz factor of the shock. So the protons, gamma protons, is about gamma. And therefore, gamma electrons, if they are in equipartition with the protons, is m proton over m electron times gamma. If the electrons are not completely in equipartition, they only have a fraction epsilon e of the energy, this is an estimate of the Lorentz factor of the electrons. Actually, it's an estimate of gamma m. So this is one thing we use. The second thing we use is an estimate of the magnetic field, and we're saying that the magnetic field energy density is a fraction epsilon b of the energy density behind that shock. So the fluid ahead of the shock has this rho. This is now energy density. And behind the shock, it's bigger by a factor of gamma squared. So we have this as well. So using these shock conditions, we have an estimate of what is the minimal Lorentz factor and what is the magnetic field behind the shock, expressed in terms of the Lorentz factor of the shock and maybe of the density ahead of it, with these extra parameters epsilon e and epsilon b, which are hopefully numbers of order unity. I think observations show us that epsilon e is indeed order unity, maybe 0.1. Epsilon b is slightly smaller. And therefore, because I know the evolution of these gammas as a function of time, I can plug it in here and tell you how all these breaks are moving as a function of time. So if you use these scalings, you have the following answer. I'll just write the answer. So this is nu c. The cooling frequency, it decreases like t to the minus 1/2. This is the peak frequency, it decreases like t to the minus 3/2. And this is the self-absorption frequency, and it's fixed in time. So this is roughly how the spectrum evolves. It's just plugging in. I gave you all the things you need, almost. You have to just plug gammas here from this. And then you have gamma of the minimal electron. You plug this in here, and with the B that you collect from here, and you have how things evolve in time. So for example, how gamma n evolves in time, it goes like t to the minus 3/2. Okay. 2 minutes, how much do I have?
2 minutes.
2 minutes, okay. So in 2 minutes, it's enough to talk about jetted explosions. Okay? What do I have to do in these jetted explosions? I just want to fix up this. Or actually this. So we see how a spherical explosion decelerates in time. We want to see if it's a jet, what will happen? So the ideas are as follows. You have a jet with an opening angle, theta. I said all angles are going to be 1 over gamma, but this one is theta. It's a given by something else, which is not the Lorentz factor of the fluid, but they will talk to each other, this theta and 1 over gamma, in a second. And let's say that theta is bigger, actually, than 1 over gamma naught, the initial explosion speed. Then, if the shock wave has moved from here to here, a distance r, how much time has passed in the lab frame? The shock is moving almost at the speed of light. So about r over c has elapsed in the lab frame. And in the frame of the shock, r over c over gamma. So if the shock was trying, the line of sight shock was trying to talk with something on the side, it had only a time of r over gamma c to do that. And if it would send a signal at the speed of light, it would only go a distance of r over gamma. Which is much smaller initially than this theta. So if you had a jetted explosion and you're an observer sitting in the middle of that jet or somewhere deep within that jet, there is no causal connection between those parts of the jet that are directed towards you and the missing part of the sphere, this, that is not at all there. So everything we have done here will be fine because the ejector doesn't know that it's actually missing its outer parts. It thinks it's part of a sphere. It doesn't have a time to know that the rest of the sphere is missing. But as time goes on, what happens to gamma goes down. The causally connected part of the sphere becomes bigger and bigger because it's 1 over gamma. Eventually, 1 over gamma becomes equal to theta. Now the sphere knows that the sides are missing and it starts spreading to the sides. This changes these scalings. And if you do a rough thing that you're saying that it's spread to a distance of r over gamma, then you have to multiply this by 1 over gamma squared. Those two gammas cancels, and basically we get that the deceleration happens almost at a constant radius. If you do a more elaborate calculation, you get that the deceleration is exponential in the radius. So the deceleration goes as r to the minus 3/2 as long as it is sphere or a wide enough jet that is wider than 1 over gamma. As soon as the jet starts to spread, gamma goes exponentially down with the radius. Still, if you translate that, a fixed radius t of the observer is r over 2 gamma squared. So even if the radius is fixed, gamma is now going as t to the minus 1/2. This is now the photon arrival time. So it's steeper than this. So a jet that is starting to spread decelerates faster, and then you can repeat this whole mechanism, but instead of plugging in these scalings, you plug in these scalings. And that will give you a faster decrease of the light curve. So I'm just giving you a hint, because I'm out of time. If you follow a single frequency, this was a spectrum. And I showed you how the spectrum evolves in time. If you sit at a given frequency, you see a light curve. And you can understand how the light curve changes in time. the light curve goes like this, as long as it's a spherical evolution. And after what we call T jet, you have a steeper decline because you change from this scaling to this scaling. If you measure this is what Andrea said in the very beginning, that this is an evidence for relativistic motion. If you measure T jet, you can know when the Lorentz factor is equal to 1 over theta. So you can measure the opening angle of the jet. This has been done for many gamma ray bursts. And we get angles of a few degrees, which means that the change from spherical evolution to spreading jet evolution starts when the Lorentz factor is a few. I think I'll stop here.
Questions? Any quick questions?
Can you talk a little bit about where the mu to the 1/3 comes from in the synchrotron spectrum?
Yeah, it's actually related. It's not a simple question, but not too tough. It's related. Do I still have it? No. Let me tell you what it's related to without giving you the whole answer. Let's talk about this gamma electron square, where it came from, okay? And it's related. So we saw that when you have an electron moving on this circle, it has a frequency. If it was non-relativistic, it was EB over m electron c. If it's relativistic, the frequency of doing this gyration is smaller. But if you're an observer seeing the radiation that it emits, it only comes from this short fraction, which is 1 over gamma. And that increases the frequency by gamma cube. The combination of those two is this gamma square. Where is this gamma cube coming from? Because that's the answer to your question. This gamma cube is coming from 1 power of gamma, from the fact that this part is shorter by a factor of gamma than this whole circle. And because the electric signal that is emitted from here and the one that is emitted from here, they're only delayed very shortly at the observer by another gamma square, because the electron is chasing the electric field that it is emitting, sort of speaking. So 1 factor of gamma from this being shorter than this, and 2 more from this chasing. So this cube. As you look at this same thing from other angles, if the observer is not here, it's a bit outside of the plane, it cannot see this short signal at all that is emitted towards the observer. So he will see some other angle theta, and there will be some theta to the -3 that is relevant to this. So the frequency that will come out of that will have theta to the -3 in the frequency. And that theta related to the frequency by 1/3, this is where this 1/3 is coming from.
So it's a geometric thing. So if you were to look at it head on, you would just see the.
If you have just a single electron and you're looking at it from the plane of the electron, you'll see a 2/3 power law. Now, this question is actually important because some people see in the spectra of gamma ray burst low frequency emission. I showed you this band spectrum. It's called, I didn't say, but it's called band spectrum. Does anyone know why it's called band spectrum? Yeah, named after a guy. He passed away, unfortunately. David Band, which just modeled the spectra of what he saw in BATSI as nu to the alpha, nu to the beta, with some smooth connection between them. So this alpha is sometimes steeper than 1/3. And people use this as evidence that this whole synchrotron theory is wrong, because synchrotron theory gives you 1/3. So what is exactly the low frequency emission of singleton is an important question.
We are ready to get started with our second session of this morning. So we have Anna back again, who will tell us about the connections between the relativistic jetted events that Raim explained to us theoretically, and how they manifest themselves in observations, and in particular how we've been getting increasingly better and better at finding them through other techniques beyond the conventional gamma ray triggers that where they were originally discovered. And hopefully we'll get into a bit about how and if LSST will help us find more of these. Okay, take it away.
Okay, thank you. Hello, everyone. Nice to see you again. As Kishale said, I'm going to do an observational overview of the diversity of transients that have relativistic outflows. I want to focus a little bit in the interest of time, and because you're going to hear about this topic in other ways later this week. So I'm going to focus on stellar transients. Tidal disruption events can also produce relativistic ejecta, but I believe TDEs are going to be covered tomorrow, so I won't talk about those. And then since this is an LSST school, I'll focus on what these sorts of transients look like to optical telescopes. These also are very bright for radio telescopes, X-ray telescopes, and so on, but each of those could kind of be its own lecture. Okay, so that's what I'll be focusing on. To set the stage, I just want to make sure we're all on the same page about what relativistic means. So a normal core collapse supernova, which you heard all about yesterday, this is an explosion, and so material is being thrown out into space. That material is called the supernova ejecta. And in a standard core collapse supernova, the ejecta velocity is about 10,000 kilometers per second. So this is, we'd say, non-relativistic. What does that mean? So non-relativistic let's say that the Lorentz factor times the speed, and I'll just, beta is commonly used to be the speed as a fraction of the speed of light, and then the Lorentz factor is 1 over beta squared. This is a common way that we talk about speeds, and then if you want to be fully relativistic, okay, the ejecta speed would be gamma beta much less than 1. And then in between, you get into this sort of awkward regime that can actually be very difficult to treat when you're doing your modeling. Sometimes you'll hear the term trans-relativistic. And that's just in between. And just for your reference, so once gamma beta equals 1 is a velocity of about 70% of the speed of light. So why would you get relativistic ejecta in a core collapse supernova? You started to hear about this from Raim already, but a common mechanism is the activity of a compact object, which is called the central engine. So that can be the newly formed neutron star or the newly formed black hole. And essentially, this provides you with another source of energy. And in the case of the neutron star, the energy is from rotational spin down. And in the case of the black hole, that energy is from accretion. Okay, so that's when we talk about relativistic events, this is what usually we are referring to. And what I will do for the rest of the session is go over what we have seen, so the relativistic events that we know very well. And then I'll talk about what theory predicts should exist in nature. And then I'll talk about the status of our searches for those theoretically predicted phenomena. And in many cases, the answer is that we haven't found them yet. But we have found some very strange things along the way. Okay, any questions about this before I go into some of the phenomena? Okay, then let's talk about the most famous type of relativistic stellar transient, which is gamma ray bursts, which you've just heard about from Raim, but I'll give a bit more of an observational perspective. These were discovered by accident. It's kind of an amazing story. In the 1960s, there were satellites designed to look for secret nuclear tests. And instead of finding gamma ray bursts from secret human-made nuclear tests, these satellites found bursts of gamma rays coming from outer space. So I think the year was 1967, and those were the Vela satellites. And since then, thousands of GRBs have been discovered. There have been entire NASA missions entirely devoted to the discovery of gamma ray bursts. So you've probably heard of SWIFT or Fermi. Those are some of the most well-known ones, but there are, probably a dozen missions that were sent up into low Earth orbit with the explicit purpose of discovering more of these events. So this has been a major, major field for a long time. Where these are thought to come from, there are basically two groups. Raim showed you the distribution of the gamma ray burst duration. So the long duration GRBs are thought to be basically from core collapse supernovae. And importantly, when we look at those supernovae, remember we talked about the spectroscopic classes yesterday. So the types of supernovae we see associated with long duration GRBs, in every case, they have had no hydrogen and no helium. So what kind of supernova is that? 1C, exactly. And specifically, they're actually all a special type of 1C. I mentioned this yesterday, but the ones with broad lines. All right, the short duration events are thought to be from neutron star mergers. And in that case, you would expect a counterpart kilonova. And that's been borne out by observations now. All right, so let's review the sort of basic model here. And I'm going to just draw the long events, but a lot of the physical ingredients are the same for the short duration GRBs. Maybe I will actually, if I'm down here, I think I'm too low, right? At the back, can you see down here? Oh, okay, fine, thank you. Okay, so basic picture, the star collapses, or the core collapses. You make a compact object. There's still a lot of dense material lying around because you haven't sort of blown everything apart yet. And so now accretion or rotation of that object powers a ultra-relativistic outflow. As it tunnels through the very dense, what remains of the star, it becomes narrowly collimated. And so you get what's often called a jet. So that jet tunnels through the star, and then it breaks out from the surface, and it goes into interstellar space. A typical opening angle for that jet a few degrees. And the Lorentz factor of that material is typically very high, exceeding about 100. If you happen to be, or I guess another way to phrase it is, if this jet happens to be pointing directly at the Earth, then you will see a flash of gamma rays lasting a few seconds. The gamma rays are coming from inside the jet itself. And then the jet collides with the ambient medium, and you get synchrotron radiation. So you heard a lot about synchrotron radiation from Rehm, but just think relativistic charged particles plus magnetic fields. So you get synchrotron radiation, and that emits all across the electromagnetic spectrum. And that's called the afterglow. The afterglow we observe, as I said, in many bands. The ones that are probably most common to observe are X-ray, optical, radio. And the X-rays are given the sensitivity of our current facilities. We'll typically see this for maybe minutes to hours, optical, maybe hours to days, and then radio, as Rehm said, can be up to years. So those are the basic stages. And then, of course, also you see if you are, depending on the circumstances, say it's close enough, you will also see the 1C broadline supernova. Okay, so that's the basic picture. And just to focus on the optical band and what's been seen.
Total number of bursts is not closer to the 4 now?
I'm sorry?
Total number of discovered bursts.
Sorry.
10 to the 3, I think 10 to the 4.
10
line.
to the 3. Oh, is it more than 10,000 at this point?
I think just Fermi is a few thousand.
Yeah.
Batsy is also a few thousand.
Mm-hmm.
And then Beposax.
Okay, yeah, maybe it's close to, yeah,
Also
maybe we're
not
close
quite
to 4,000 now.
10,000, but almost there. Yeah.
Yeah, that's quite possible. All right, so optical transients. All right, so there are a few things you can see. One of them is the 1C broadline supernova. The duration of an optical supernova light curve we talked about yesterday, that's primarily set by the radioactive decay of nickel-56. It's also set by how long it takes the photons from radioactive decay to diffuse out of the optically thick ejecta. And altogether, that's why the supernova emission lasts for several weeks. You can see the afterglow, which I just mentioned. And that is much faster because the time scale here is governed by this optically thin synchrotron. This is very, very different mechanism. So behind you, I have an example of an optical afterglow. This is a light curve of an afterglow to a known gamma ray burst that was discovered in 2014. And the horizontal lines show you the sensitivity thresholds of several different wide field optical surveys. And so the message of this plot is that within just a few hours, the afterglow fades below the sensitivity threshold of the survey. And so that's later on, I'll talk about how that makes it very difficult to find in survey data. And then this afternoon, you're going to do an exercise of finding afterglows in data from ZTF. Okay, one more thing you can see is a very, very fast minutes duration, very, very bright optical transient that could be associated actually with the prompt gamma ray burst. So the spectrum of the gamma ray burst does extend to the optical, but it has to be really bright to see it in the optical band. You can also see what's called the reverse shock, which also is very short-lived. I won't talk a lot more about that today, but I just wanted to mention it because it's a sort of distinct emission component from what I wrote above. And there's a famous case. Oh, actually, maybe I have. Did I show plot it a bit? Oops. Yes. Okay. This is a very famous case of that. So this is Judy Rakusin's paper in 2008. And so what you're seeing is the black sort of solid line. That's the gamma ray burst. So that's detected by a satellite called CONUS Wind. And then the points with error bars, that is actually from an optical telescope. And so this was a case where the gamma ray burst was so bright that it was detectable. And if for the optical observers, if you look on the right, it reached 5th magnitude. So this was actually a naked eye gamma ray burst, or at least the optical part was could have been seen with the naked eye. So very, very rare to catch something like that, but there have been a handful of cases. Okay, I think that's basically most of what I wanted to talk about with the GRBs. Oh, maybe I'll also, just while we're looking behind, show you what the spectrum looks like in the optical band. So the spectrum in the optical band, this is a power law. So we would say, yeah, so this is just a power law. And then you see superimposed on the power law absorption lines, which are labeled here. And those absorption lines are from species that are in the galaxy in which the burst happens. So this is at a redshift of 1.5 or something. And so as the optical emission is leaving its host galaxy, you get this imprint of the kind of composition of the material surrounding the gamma ray burst. Yeah, yes.
Do all GRB afterglows have the same like power law spectrum, or do they have different like indices?
Yeah, that's a good question. So the question was about the, I guess, the spectral index of the optical afterglow. Is that right? Yeah, so it can vary. Raym talked about this a little bit, but basically when you picture a GRB afterglow, what you should picture is a series of connected power laws, something like this. And these parts where the power law index changes are called break frequencies, synchrotron break frequencies. And the order of the break frequencies depends a little bit on how long you are after the burst and some of the physical properties of the burst and its environment. You might have down here the self-absorption frequency, characteristic electron frequency, the cooling frequency, something like that. And so the spectral index that you see is directly reflecting where is optical in this. But this whole thing is moving over time. So over time, you might expect to see a change in the spectral index, but it's not, it can't be, it tends to follow there's certain rules governing this that Raym has worked out in a lot of detail. And so it's usually not just anything. Yeah. Yeah.
So where does the like optical prompt emission come from? Is it like thermalized radiation?
Right. So that's a very good question. In the case that I showed, so yeah, just taking a step back. First of all, there really aren't that many cases of this. One of the really amazing results that you should take a look at. So TESS, the satellite, the TESS team has done some work looking at their data in the aftermath of known GRBs. And they've seen several cases with very, very bright detections that were very short. But the TESS cadence of that data something like 5 minutes. So they're usually just one detection. And so they don't know exactly what it is. Is it somehow, if you take, so first of all, no one really also knows what the prompt emission is. What's the mechanism? Is it synchrotron? You know, what is it? So we don't even really know that in the gamma ray, let alone then in the optical. But they try to, in the test paper, they try to connect the gamma ray spectrum with the optical. In some cases it works, and in some cases it doesn't work at all. So I think the short answer is we don't really know. Yeah, so especially when they think it's truly prompt. But then there are cases where it's thought to be from what's called the reverse shock. And that's maybe a little bit better understood because that's supposed to be synchrotron. And that is very similar to, so the afterglow I mentioned, that's coming from the jet's collision with the ambient medium. So this is the circumstellar medium or the interstellar medium. And so you get, the collision makes radiation. But in addition to having this collision traveling, this shock wave traveling forward, you also then get a shock wave traveling backwards back into the jet. And that also makes radiation. That's called the reverse shock. So there are some cases where it's thought to be from that. But I think the short answer is it's not really known. And especially because in certain cases, we have very, very limited data on it. Yes.
Why is it that like only one C's get the velocities needed to be relativistic or like have GRBs? That
is a very good question. That is what I'm going to talk about next. So I'm going to just hold off on that. Yeah. Actually, out of curiosity, who here works on something that they would call a relativistic transient? What do you work on?
Bots and once EDLs.
Okay, all right. And I guess I know.
If we ever find a jetted TDE that.
Okay, so the TDEs. What about you?
Jetted by the AGN just embedded in black holes.
Okay, AGN. So I think that's Thursday. That's later this week, right? Yeah. Who else? Yes.
TDEs.
TDEs.
GRB
supernovae.
Magnetar flares.
Magnetar flares. Okay. I'm actually not. I think that's one thing that maybe is not covered. So we'll have to ask you to tell us about it. Anyone else? Okay. So GRBs, TDEs, AGM. All right. Yeah. So let's talk about exactly that question. Why is it that we only see, when we go and we hunt down these long duration GRBs in the nearby universe, why do they all have supernovae that look pretty similar to one another? So a good place to start in this discussion, I think, is with rates. And these are all going to be rates in the local universe. Whenever you give a rate, you have to be careful because the universe has evolved a lot over time. So the conditions around here and the conditions at a redshift of 2 are very different. Galaxies were different, and so the rates of transients will be different. So I'm going to quote rates in the local universe. And this is actually, this is pretty new information. We have not had good rates, I would say, until the last couple of years for these phenomena. Okay, core collapse supernovae, about 10 to the minus 4 per cubic megaparsec per year. The 1C broadline supernovae, about 10 to the minus 6. I'm being a bit, this is sort of order of magnitude. It's more like 3 to 5% of the core collapse supernovae, so maybe a few times 10 to the minus 6 per cubic megaparsecs per year. Okay, now GRBs, and here I'm going to say GRBs on axis. So GRBs, because if you see the GRB, the jet had to have been pointing directly at the Earth. This rate is about 10 to the minus 9 per cubic megaparsec per year. Or a number, it's 1, convenient to remember, In gigaparsecs per year, it's about 1. Now, of course, that's not actually the rate of GRBs, because I mentioned that the width of this jet is just a few degrees. So for everyone pointing at us, if our basic understanding of GRBs is correct, there should be way more pointing in other directions that we're just not seeing. And the way that you convert the factor is where should I write this down? Okay. That conversion factor is 1 minus cosine of the width of the jet. You'll see terms beaming factor, beaming fraction, and for typical measurements of that opening angle of a few degrees, 10 degrees, the number pointing away from you for everyone pointing at you should be about 100. So it may give you about 2 orders of magnitude. So 10 to the minus 7, let's say, cubic megaparsec per year. Okay, so what can we see from these rates? We see, first of all, that even if you correct for the beaming, the fact that most of them are pointing away from you, typical numbers will still get you about a factor of 10 from the 1C broadline supernova rate. So actually, most 1C broadline supernovae, just from these rates, are not making any GRB at all, which is consistent with the fact that observationally, we've tried very, very hard to find evidence for jets in 1C broadline supernovae, even ones without GRBs, with no success, or okay, not zero success, but pretty limited success. It also is showing you that it's very, very rare for a core collapse supernova to make a GRB. So now you have a 3 order of magnitude gap. And so this raises a fundamental question in the field, which was exactly what was just asked, which is why do, or I guess one way we can phrase it is, why are GRBs rare? What are the physical conditions that cause some core collapse supernovae to make a GRB while others do not? Why are some core collapse supernovae 1C broadline supernovae? Why actually do only some 1C broadline supernovae make GRBs? Is this a is it more like a continuum, or is this some very distinctive thing that only happens in a very rare fraction of cases? So one answer to this question you could imagine is that actually, fine, GRBs themselves are rare, but maybe GRBs are a very extreme thing. Maybe it's actually very common to have a jet of some kind. It's just that most of these jets don't make gamma ray bursts, so we're not seeing them as gamma ray bursts. And so maybe you could actually accommodate a much higher fraction if you called this relativistic jets instead of GRB. Maybe that rate would be much higher, and you could actually make it much closer to some of those rates. Does that make sense? So a very related question is there a sort of GRB supernova continuum? Yes.
Given the high uncertainties with intrinsic GRB rates, is this robust to say that we certainly know that not all 1C broadlines can harbor a GRB?
Yeah, that's a good question. So I would say these rates are fairly well known. The top 3 are well known, but you are right that this rate is not well known, because to really measure this rate properly, you would have to find the ones that are off axis. However, this is a ceiling in a sense, because we have not seen any other type of supernova associated with GRBs. And so either the problem is worse, or you could say, okay, maybe actually all of them have this, but we also know that's not true because we follow enough, we search for off-axis jets in these, and there are some cases where you can rule out a jet with reasonable parameters. Does that answer your question?
Yeah, thank you.
Okay, yeah.
Are the rates here you're quoting just for long GRB, or do you include
long GRBs? Yes. Yep. Yes.
If you remove the prompt emission, is the afterglow roughly the same brightness if we're on axis versus off axis?
I will talk about that next. Yes, I'll come back to that. Yes.
So just to clarify, is it true to say that all of the long GRBs have one CBL like supernova?
I think the accurate statement would be of the long GRBs that we have seen in the relatively nearby universe, so redshift less than about 0.1, 0.2, most of them do, but some of them don't. So famously recently, there have been some long GRBs with kilonovae. And so actually, those are probably not this. Those are probably compact object mergers. There are also some famous cases of long GRBs with nothing to very, very deep limits. And it's not clear what those are. So it's not all, but I think by number, it seems to be most. Yeah. Yes.
Is the supernova intrinsically brighter than the afterglow?
No, the supernova is much intrinsically fainter than the afterglow. And the reason is that when you have material traveling towards you with very high Lorentz factors close to the speed of light, a couple of different effects come in to really boost the luminosity. Relativistic beaming. So photons that were, if you have, imagine a jet kind of spread out like this, what you're seeing ends up being, it all gets squeezed together basically, so your intensity gets higher. And the Doppler boosting. So there are a couple different effects that make it very, very luminous. So afterglows, you can see out to, I mean, optical afterglows, you can see out to a redshift of, I don't know, 7, 8. But you're definitely not seeing a 1C broadline supernova out to redshift like that. Yeah. Yeah, the relativistic boost you get makes these things, you can see them out basically to the other end of the universe, which there's a whole history of using them as cosmological probes to study galaxy evolution in the early universe and so on. Yeah, that's a great question. So if you're looking at it on axis, it actually can be very difficult to see the supernova because you have to pull it out of the after. Sometimes it's buried under the afterglow. Yeah. You'll see it spectroscopically, and so then you can sort of people decompose what you're the light curve. Yeah. Any other questions? Yes, Kishale.
What constraints do we have on jets from non-1C broadline core collapse supernova?
Yeah, that's a good question. So I would say, so there have been, and maybe a bit more historically, because before, these are very rare supernovae. And so what people did initially was just take kind of all stripped envelope supernovae, follow them up, look for evidence of jets with basically no successes. Another row I could put on here would be rates from blind radio searches. So people have looked for jets, say in the VLA Sky Survey, and the rate that they get is very similar to this rate. And so that tells you, that suggests that there's not actually that, which is kind of skipping ahead a little bit to the answer, but yeah. So I think maybe somewhat indirectly, but it's there are multiple avenues, I think, converging on a picture where most of these also don't have successful, at least successful GRB-like, GRB energy types of jets. Yeah. Any other questions at this stage? Okay, yeah, some of this is getting to, I'm sort of skipping ahead a little bit of what I was going to talk about. Okay, so let's, I'm gonna focus a bit on this now. So why might there be such a continuum? What sorts of objects might exist in that continuum? I'm gonna get to some theoretical predictions. And I'm going to start with something that Raim discussed. Which was pair production in GRBs. So Raim made the point that in a gamma ray burst, you have some enormous amount of energy in quite a small volume. And so your photons should actually pair produce. So I drew this diagram of the 2 photons coming in. And making these pairs. Right? So this pair production, you can write an optical depth to that process. and it's something like 10 to the 15. And what that means is that the gamma ray spectrum you observe really should be thermal. It should have been thermalized because you should have this enormous optical depth to this process. But the observed gamma ray spectrum in almost all cases is non-thermal. And so Raim gave you the answer to how you can reconcile these things. And that is that the velocity of the material is very large. And once you are really relativistic, then all these factors come into play. We talked about the relativistic beaming, but another thing is that you really reduce the effective optical depth. However, if you say you want to have some huge Lorentz factor, you have another constraint, which is that given the energy budget of your system, if you want the Lorentz factor to be super, super, super high, this mass has to be really, really, really low. And the mass you get for GRBs is around an Earth mass. And that's long been considered strange and maybe a little bit contrived. Maybe it's just contrived because we infer this, we see a gamma ray burst, and just kind of by definition, you end up with this very low mass. This mass refers to, by the way, the mass of material that's been put in the jet. So the jet is accelerating something, or the central engine is accelerating something in this jet. So what's the mass of that material? And so perhaps it's actually way more common to have a lower Lorentz factor, more material in the jet. But in those cases, maybe you just wouldn't make a GRB as we know it. And so our Swift, Fermi, these satellites designed to look for GRBs would just not see them. And so this very low mass thing, the word that's sometimes used is clean, has to be very clean. But maybe these dirty fireballs are more common. So there have been a number of sort of predictions in the literature about what a dirty fireball, dirty jet would look like. And they include that you would see what looks like a GRB afterglow, but maybe there just wouldn't be a GRB because of this pair production issue. And the word that's often used for an afterglow that has no GRB is an orphan afterglow because it would not have a parent GRB. Okay, so that's one prediction. And you could imagine if these are 100 times more common than clean GRBs, suddenly you could have a situation where you're at 10 to the minus 5 and you're actually getting to a situation where you're more common than 1C broadline supernovae. All right, I'm going to leave these rates up for now. All right, what else might be out there in the universe? Another prediction is that many of these jets might sort of exist and be formed, but then not actually escape the star. And so the term that's often used is a choked jet. And this seems, it's not hard to imagine that this exists because to escape the star, the duration of the engine, so if it's a black hole, the amount of time that that black hole is actively accreting and powering the jet, that has to go on for longer than the time it takes for the jet to get out of the star. Because the star is very, very dense. So picture something like a drill. You're kind of drilling through this really dense thing. So you have to keep powering it for it to get through. If you just turn off the power, it's not going to make it out. And there's no obvious reason why this should be the case. It's just that it has to be true for us to then see the gamma ray burst. And so it seems quite natural to think that much of the time this is not obeyed. And again, you could imagine if it's 100 of them for every one that gets out, suddenly you're in a situation where maybe you could have jets in other types of core collapse supernovae, and they just didn't get out. And that actually might make sense because 1C supernovae are the most compact progenitors. So they're missing their hydrogen envelope, they're missing their helium envelope. The radius is much orders of magnitude smaller, like four or five orders of magnitude smaller than some of these supergiants. And so that might give a natural reason why you're not seeing successful jets in other types, because maybe it just has to do with something, maybe it has something to do with how long it would take the jet to get out and how long these engines typically operate. So that's been a common hypothesis in the literature. Yes, you look like you want to.
Associated with low luminosity GRBs?
Sorry?
These are sometimes associated with low luminosity.
Yes, I'll talk about that in a minute. So I would say, low luminosity GRBs are a well-established phenomenon observationally, but they themselves show quite a lot of diversity. And so mapping them back onto some of these predicted phenomena, I think, is not so straightforward. Yeah. But I'll talk about that more in a minute. Okay, so what's this? I talked about sort of predicted appearance. I said a dirty fireball might look like an orphan afterglow. Here, the appearance would be different. You don't expect something like this, because for this, you really need this successful thing to get out. If the jet is choked inside the star, it's going to very quickly lose its structure. It will just become much more isotropic, and it will kind of give its energy to this stellar material. And then it will, you'll get sort of it'll deposit it as a shock, and then you'll have some kind of shock breakout. So common predicted appearance, but it won't be a normal shock breakout. This might be a relativistic. And in the optical band, since that's what we're focusing on, you might expect to see some kind of shock breakout or shock cooling emission. We talked about that quite a lot yesterday. So picture this early kind of thermal black body emission before the primary, much faster than the primary supernova light curve. Yes.
So if the choked jet is sharing its energy with the rest of the sort of supernova ejecta,
yes,
are the 1CBLs that don't have an associated GRB have broader lines?
That is a very good question. Okay, two things I'll say to that. One thing is, so no, observationally, Mariam Mojaz has done work on this, and I think she actually found that, if anything, I mean, the problem is the number of these things is quite small, but I think she found that statistically, the ones with GRBs might even be a little faster, if anything. Another thing to mention is that in the case of a GRB supernova, one thought is that the thing that's actually triggering the explosion is not the conventional neutrino mechanism, but it's actually the jet. So there have been some simulations showing that if you make this kind of jet in a star and you tunnel it through, it will actually cause the star to explode as something that looks kind of like a 1C broadline supernova. So yeah, that's the other thing I would say.
So an energetic jet would imply a more energetic 1CBL.
So that's what you'd think, but then work has shown that that's not true. Yeah, so that's also a problem. Yeah. Yes.
Also, this shock breakout wouldn't necessarily be relativistic, right? If the jet is choked very early.
Yeah, I guess that's true. Maybe I shouldn't have. Yeah, right. Yeah, that's true. Yep, that's true. Yeah. Yes, yeah, that's true. Yes.
How often, like the orphan afterglows, like do we see them really often, or like?
I'll get to that. Yeah. Any other questions? Okay, there's one more phenomenon I want to mention, and this gets to the question that was asked about how the off-axis afterglows compare to the on-axis afterglows. I'm a little sad to erase this, but that's okay. Okay. Can always summon it back up if we need. Yeah, so I'll talk about this one more predicted thing, and then I'll tell you what we've actually found. this is not quite the same category because I've described this predicted continuum that may or may not even exist. This better exist. Otherwise, we've really, we have something very, very wrong in our whole GRB model. Right, so the picture here is you have this jet.
We've also seen at least one.
In a short GRB.
Yeah.
Yeah, that's true, but not in a long GRB. Okay, so this is our initial jet. And the point is that as it collides with the ambient medium and it decelerates, you start to get different effects that kick in and the jet will spread. Okay, so this is what's happening over time. And so if you were an observer out here, initially you would not have seen anything, right? So early on, only observers here would have seen something, but then as it spreads, suddenly you're starting to see the synchrotron afterglow. And what this looks like observationally so an on-axis afterglow, this is in linear space, there's a power law, but in log space, it'll be a straight line. This is on-axis. And then maybe I'll use a different color here. So off-axis, first you see nothing, but then you'll see a very steep rise. And then eventually it basically joins the on-axis light curve. And the peak here is when the Lorentz factor drops to 1 over that initial opening angle. So the question was, which one's brighter? And you can see that early on, before this peak, the on-axis one will be brighter by many, many orders of magnitude.
This is 1 over the offset angle.
Oh, I'm so sorry. Yes. Yeah. Sorry. Yes, obs, not. Yep. Okay. Sorry about that. Right. So the this. Yeah. Thank you. Right. So the further off axis you are, the later it's going to join this thing, and the fainter the peak will be. That's very important. Okay, so those are 3 sort of theoretically predicted phenomena. And for all of these things, you're basically saying, okay, we know about GRBs. There's some essential ingredient to them, whether it be geometry, they better be on axis, whether it be their Lorentz factor, it has to be extremely large to explain the non-thermal gamma ray spectrum and the high energies. And it has to actually escape the star. And then you say, well, why does that have to be true? Maybe actually most of the time it's not true. And then you might end up with ways to get a much more diverse landscape of relativistic stellar transients. And now I'll start talking about what we've seen. Yes.
How broad can the jet start to get as it dies and it still be a jet?
Yes. So how broad can it? So at what point would you no longer call it a jet? Is that what you're saying?
Yeah.
It never stops being a jet.
Oh, you want to explain why you think that?
Yeah, so I studied the hydrodynamics of these relativistic jets, and they actually kind of, the way they spread is that they don't spread exponentially. So the Lorentz factor decreases exponentially, but they spread sub-exponentially, which is why when they become non-relativistic, they still have a pretty collimated structure. They're still pretty narrow. Possibly after that they spread, but you get to a point where you have a Lorentz factor of 1.5. And it can, and for like reasonable initial GRB opening angles, it can still be very collimated.
Okay, thank you. Yes, Sam.
So from this plot, it's some average apparent GRB like magnitude, you could back out based on the sensitivity of our current missions, like what angle we are sensitive to?
Okay, yeah, so that's a good question. The problem is that the evolution of this depends on a lot of things. It's very sensitive to the energy of the jet. It's sensitive to the density of the ambient medium. It's sensitive to the opening angle of the jet. And once you start introducing all of these parameters, you get into situations where you just have huge degeneracies. So if you had that alone, you wouldn't know. Yeah. If you have a very, very, if you have a very, very low density medium, for example, this thing will just rise forever. Yeah. Yes.
What is the low density to?
Typical density for from GRB afterglow modeling is about 1 part per centimeter cubed. But people have inferred densities that are like 4 orders of magnitude smaller. So I'd say anything much lower than that 1 per cubic centimeter would be low. Yeah. Any other questions about this predicted landscape before I talk about the observed phenomena? Okay, right. So I'm going to talk about a bunch of different things now. I would say right now we have a whole zoo of things, and I will let you form an opinion about what you think might map onto what, because I'd say we don't really know. Oh, there it is. Okay, let's start. Let's see, where should we start? Let's start with the low luminosity GRBs, since somebody already brought those up. Okay, so basically within the nearby universe, that's the place where you can actually see gamma ray bursts and also the 1C broadline supernova, because once you get to too high redshift, you basically lose the ability to see the supernova. And it turns out that within that volume, most of the GRBs that we've seen have not been what we call a classical GRB that you've been hearing about from Raym and from me, but you'd call it a low luminosity GRB, and they have some properties that are actually very, very different from classical GRBs. Okay, so their luminosity is more like 10 to the 46, 8. So just in terms of gamma ray luminosity, they're orders of magnitude less luminous than GRBs, which is where the name comes from. They have some very, very famous examples. Actually, some of the most famous GRBs are low luminosity GRBs. GRB 980425. So you might have heard of some of these. Supernova 1998 BW. This was the very first time we had a supernova and GRB observed together. Super 2006 AJ. This is a very, very well observed event, modeled as a kind of relativistic shock breakout. These are not normal GRBs. One thing that's not normal about these is that when you model them, they have luminous radio emission. But when you model these events, it's typically inferred that these were not highly collimated jets, but more sort of quasi-spherical relativistic ejecta. So just morphologically, it's very different from a classical GRB. And then there were early claims in the literature after the discovery of these two objects, so based admittedly on small number statistics, that the rates of these things intrinsically might be 10 to 100 times greater than regular GRBs. And so that, I think, is one of the claims that got people really excited about these things, because that fits the description of some of these predicted phenomena that you might expect to be more common, like a choked jet or a dirty fireball. Yes?
Can you explain why you're labeling the L as isotropic?
Oh, yes. Right. So this is sort of a, right. So the way that with GRBs, energies and luminosities are often quoted is because what you're seeing is actually just from a narrow cone. But a point Ray was making is that when things are moving relativistically, you actually, just from looking at it, you would know the difference between this and a sphere, because you have no information about what's outside this. And so this iso is shorthand for isotropic equivalent, because it means that you're assuming that this thing is coming out as a sphere. So you're not making a correction for the fact that it's a cone.
Is that basically the observed luminosity if you knew the distance?
Right.
Okay.
Yeah. Yeah, but then it's not correct.
Yeah.
Yeah. But yeah, yes, it's a more model agnostic way to do it. Yeah. One other thing I'll just mention. Oh, maybe do I actually have? Yes. Okay. This is the really famous 2006 AJ. It had really beautiful data. So it was discovered using Swift. And the whole point of Swift completely revolutionized GRB studies, because not only did it have the discovery machine, it also had the follow-up machine. So on the same spacecraft, there's a thing that discovers GRBs, the BAT burst alert telescope, but then it has a follow-up X-ray telescope and a follow-up UV optical telescope, which I think is an important lesson to us all. So on the top, you can see the GRB is that first pulse of X-rays. And then you see this power law, which is basically the afterglow. And then if you look below, you see this pulse, two pulses. That first one is the sort of shock breakout, shock cooling emission. And then the second one is the radioactive decay, usual nickel 56 supernova. And there have been many papers that modeled this event. And the thing that's really weird, we mentioned this yesterday, is that the radius you infer is like 3 to 4 orders of magnitude greater than what you would nominally think the radius of a 1CBL progenitor would be, which should be about 10 to the 10 centimeters. And to my knowledge, I don't think there's been a really satisfactory explanation for that, but that's important to keep in mind when you're thinking about what these things might be or what their physical connection to GRBs might be. Okay, so that's luminosity GRBs. There are also, of course, the 1C broadline supernovae, which we talked about yesterday. At this point, there are probably 200 of these known, of which maybe tens are kind of well studied. These, by definition, have fast ejecta. So I mentioned that a normal core collapse supernova has an ejecta velocity of about 10,000 kilometers per second. And a 1C broadline supernova, that can be 2 or 3 times as fast. And a normal supernova has a kinetic energy of about 10 to the 51 ergs. But in a 1C broadline supernova, it's often about an order of magnitude greater, although not always. One thing I will say is that from kind of the population demographics that we have now of the 1C broadline supernovae, something very interesting is that so most of them, yeah, so same. Which direction? Okay. So peak absolute magnitude in the optical, most of them are what I would call faint events. So they're greater than this. Then there are the luminous ones. The luminous ones are The luminous ones are 10 times less common than the faint ones. And when we have followed up GRBs, we've only found luminous ones. So that's something else important to keep in mind. Remember, there is maybe a roughly factor of 10 gap also in the rates. And then one last point I'll just make is that they do show actually a lot of observational diversity, a lot more than I think was recognized prior to just a few years ago. Some of them have light curves powered by shock breakout or shock cooling. Some of them have normal light curves powered by probably radioactive decay. Some of them have strong X-ray radio. But very, very few, most of this is from CSM interaction. Very few show evidence for relativistic ejecta. And it seems to be at less than the roughly 10% level. All right, let's talk about orphan afterglows. This is a very difficult task. So to find an optical orphan afterglow means you have to find it without the benefit of a gamma ray satellite telling you where and when to look. And in the vast majority of optical afterglow discoveries, the way that they do it is they wait for a satellite to find the GRB. And then if you point to that location, you'll find the afterglow. So that's much easier. But of course, to find the orphan ones, you have to do it blindly. And one of the big changes that high cadence surveys like ATLAS and DTF made is that it finally has become routine to actually find these. So we have now about 10 examples. There's also a very nice candidate from radio surveys, but the problem is that from radio surveys, the radio afterglow is much slower. So you'll identify it like a decade after the supposed initial burst time, and we don't have any information, there's no supernova. It's too late to go back and see what happened. Whereas optical afterglow, you're finding it within the first few hours. So there's time to actually get follow-up observations. Okay, so what have we learned from some of these, just in case you want to look up some of their some of these objects? Famous one was PTF11 AGG. This one had no redshift measured, and so it's kind of hard to really say exactly what this was, but it had a very luminous radio afterglow, so it's almost certainly a real afterglow. Two other very nice ones. Uh, 2025. I'm listing these two in particular because these are, as far as I know of these 10, the 2 cases where we can really convince ourselves that this was not a regular GRB afterglow. The problem is that when you try to model these things, you get a degeneracy. So this is a plot from a paper from earlier this year showing the multi-wavelength afterglow of 2021 LFA. So the optical afterglow, the optical light curve is on the left and the radio light curve is on the right. And the 2 columns are showing exactly the same data, but the 2 rows are showing exactly the same data, but with 2 different models. And it turns out that you can actually explain it in 2 different ways. You can explain it with a dirty fireball, so an on-axis jet with a low Lorentz factor, or you can explain it as an off-axis regular GRB with a high Lorentz factor. So this is a very interesting event because we know for sure it's not a regular on-axis GRB, but it turns out that it's actually very difficult, even with beautiful data, to tell the difference between these 2 possible scenarios. But it's exciting because it's almost certainly at least one of those 2. All right, and just to add that all of this has been enabled by fast transient searches in optical survey data, and that's what you'll be doing in the afternoon module later today. Yes.
So why should the radio afterglow be so much so delayed compared to the optical?
Right. So that's a good question. And going back to that cartoon that we drew earlier of the synchrotron spectrum. So radio is way down here. And then you can kind of picture, this is a little oversimplified, but if you picture this whole thing moving left with time, that's going to rise over time. Whereas if you start at the optical, higher frequencies will be a little brighter earlier, and they'll peak a little bit earlier because this whole thing was moving right to left. That's roughly one way you can think about it. Yeah.
The time scale should still be similar to the deceleration time, because I think you mentioned like years or something later.
Oh, so years, by that I mean how long it's detectable, not how long it takes to peak necessarily. Yeah. Yeah, so the years for the discovery of the radio afterglow. Yeah, okay, so that has to do with the cadence of radio surveys,
okay.
Which is very, very slow. Yeah. Yes, yeah, good question. Any other, yes?
I do both the models of the late time radio emission underpredict.
Oh yeah, these models, especially at low radio frequencies, which I think is where it usually, let's see, oh no, it's higher frequencies. Yeah, I'm not entirely sure. These models don't take certain things into account, and especially in the radio, you can have weird effects like at lower frequencies, you can have scintillation, you can have self-absorption, which this is not even doing. So yeah, I don't know exactly why for this, but there are certainly things that can happen that are not being accounted for here. There can also be, this kind of modeling is very complicated because these jets can have multiple components. You can have a really highly relativistic core component, and then you can have a less relativistic component that's kind of a sheath around the jet, which can carry a very similar amount of energy. And so you can actually have both things contributing and evolving in slightly different ways. So it can be really, really complicated. Yeah, it's almost a miracle that these work as well as they do. Yes?
It looks like the maybe early data would be better for distinguishing those 2 models. Are there other better probes like UP or?
Yes, okay, so right. So how could you actually solve this problem? One of the differences between the 2 models, if you look at especially the optical, is that they find a different best fit burst time, but you just don't know the burst time because there's no GRB. But that's a big degeneracy. So if you had much higher cadence data, then you could do much better because you would remove one of the parameters that the models are degenerate to. Or if you actually had the prompt emission, you would solve this problem. And a dirty fireball, actually both a dirty fireball and an off-axis GRB should make some very early soft X-ray emission. And so I personally think the best approach to this is not with optical discovery, but actually with X-ray discovery. So Einstein probe and SWAM, these are new X-ray missions that launched last year, and they found tons of X-ray transients. And so that helps you for two reasons. If you can find the prompt X-rays, one is that you actually know the T0, which then solves one of the big degenerate parameters. And it gives you more information because if you're on axis versus off axis, you should see different early X-rays. So if you're off axis, the X-ray should be an afterglow. So it should be a smooth power law kind of thing. But if you're on axis, you should be seeing GRB prompt emission, which is highly time variable. And so it should also look different. So I actually think that's probably the only way to do it. Yeah.
And the optical light curve will also look different at very early times. But to get the peak to like, they have observations here at less than 1/10 of a day.
Mm-hmm.
So to get much earlier times is going to be difficult, and to get the peak to be later, you need to go to larger observing angle. And then it's also going to be much fainter,
yeah,
and more difficult to detect. So in principle, if you have the complete light curve at early times, that will almost always break the degeneracy with an on-axis dirty fireball model. But you need early times.
Yeah, thanks. Anyone? Yeah.
So like in the case of the dirty fireball, if it's contaminated with stellar material, like
yeah,
at late times, should you expect to see like mines or something?
Yeah, that's an interesting question. We don't really see with the composite, you're asking about, could you see something spectroscopically about the composition of the jet material? I know it'd be very, very difficult. Yeah.
Diluted with
yeah, you're not really seeing, in the spectra of GRBs, you're not seeing anything about the material in the jet. You're just seeing absorption from cold stuff that's lying around the jet. I don't know that maybe there's some way you could look for the composition of the jet itself spectroscopically, but I don't know what that would be. Any other questions about these phenomena? I only have one more to go over. Okay, yeah, so I would say, choke jets, dirty fireballs, off-axis GRBs, it's possible we've seen them, but it's been difficult to map the observed landscape into some of these theoretically predictive phenomena. Oh, but one important point is that you can say something about rates because we have about 10 of these orphan afterglows, but they're only about half of the afterglows that we have found. So in our optical surveys, we routinely find afterglows, but about half the time we realize that they were just GRBs. So if it were true that there were like 100 times more dirty fireballs than GRBs and they had similar jet properties, we can basically rule out that scenario. Okay, so last one I want to mention, sometimes called luminous fast blue optical transients. So these are a little bit different. They're not afterglows. So afterglow emission, I mentioned, is synchrotron radiation. The emission here, as the name suggests, this is blue. So this is thermal radiation. There are about 14 of these discovered so far. The most famous example, sort of prototype, was the transient AT2018 COW, which was discovered by the Atlas survey. And sort of key characteristic is that they are very, very luminous across basically the whole electromagnetic spectrum. Luminous X-ray emission, their optical emission, as the name suggests, is more luminous than typical supernovae. The radio emission is also more luminous than typical supernovae, all by orders of magnitude. So these are a big mystery. We don't really know what these are, but there is evidence for very fast-moving material. Say transrelativistic. So from the radio, we've seen velocities something like 0.6 c. Yeah, I think 2020. The optical, we've seen optical flares lasting just a few minutes each with supernova luminosity. So this is one of the best observed such examples. So this is with a special kind of optical telescope, a high-speed photometer that has very, very little dead time between individual exposures. And so you can get a very, very, very high cadence light curve. And so these sorts of flares were seen 100 days after the initial transient. They're probably synchrotron in nature. So it's probably something kind of like a GRB, except goes on for 100 days and it's in the optical. So extremely strange, but from that you can also infer, something like these sort of transrelativistic outflow speeds. And then they also have X-rays at the level of 10 to the 44 ergs per second, which they can show high variability. And it's just strongly reminiscent of relativistic jets, even if there's no direct evidence for that from the data. And then one more thing.
Any periodicity in these highly variable light curves?
None that has been really, none that I would say is really widely agreed upon. There were, for 18 Cal, there were some claims from the X-ray data of of oscillations. I can't remember the frequency, but I think it's sort of low significance, and people sort of disagree on how robust it is. And I don't know of any. I don't think there's any other indication of periodicity. or at least not strict periodicity. Any other questions about these objects? Okay. Then I will just, we have 15 minutes left, so I'll wrap up by talking about a few future surveys, and then I can just take some questions. All right, so what's the kind of observational frontier? This is a fun area to work in because it's inherently very multi-wavelength, and there's sort of an explosion of surveys at pretty much every part of the electromagnetic spectrum. I think discoveries at higher energies. So I mentioned the soft X-ray. Somebody mentioned the UV. We have not had those capabilities in the case of the UV, basically ever. In the optical, it's going ultra high cadence. And there are facilities being designed to do that. We were just talking about the Argus array. There's also LAST. And together with much slower surveys that reach much greater sensitivities like LSST, these become, you get really a complete picture of the optical behavior. And then I think earlier discovery and follow-up. I mean, that's enabled by these things. The higher the cadence, the earlier you can identify. The higher the energies, the earlier you can identify. But another really important thing is photo Z estimates from galaxies, and we'll have that much better also with LSST. And then also, I'd say, radio surveys. Should help us with our, especially the off-axis jet problem. Okay, so we have 10 minutes left. I'll just leave it at that, and we can I'll take any remaining questions that you have.
What do you think are the progenitor system for the cow-like transients?
Yeah, so I sort of deliberately didn't say much about that because I don't really know, but I think the main thing that distinguishes them from at least traditional models for, say, GRBs is that I think you almost certainly require the progenitor to be a binary system for various reasons. So one of the models that, for example, Brian Metzger developed was the merger of a star and a compact object. Which almost ends up being like a little mini TDE. You can ask him to defend himself when you see him later. But the reason I think this is because, so first of all, these are pretty much all in star-forming galaxies, and they're off nuclear. So that suggests a link with massive stars. But they all seem to have very, very similar structures to their ambient medium. So Cassie's work has shown that their radial light curves are actually very, very similar to one another, which is very strange because for supernovae, they have, I mean, their radial light curves can do almost anything. And that reflects huge diversity in their circumstellar medium properties, but does not seem to be the case with these objects. Radial light curves all peak at basically the same time, and then they fade away again at almost the same rate, which is very strange. And so the nice thing about Brian's model is that it sort of more consistently predicts a similar kind of medium because that medium you make from this merger is tied to the explosion. So that's probably, I don't know exactly what's merging with what, but I think something like this is probably my preferred scenario at this point. Other models that have been popular, one is of a failed supernova. So, blue supergiant or something that does not successfully explode, but I don't know how you explain how similar the environments are. So I don't prefer that as much. People also have tried tidal disruption events of intermediate mass black holes. Again, I don't know why. I don't think that really explains the radio light curve behavior. And it's actually very similar to this. It's just the black hole mass. So, yes.
You said that earlier that radio surveys are inherently very low cadence. What is the range of that cadence?
Yeah, so I don't mean inherently as in there's some fundamental, like you just absolutely could not make a higher cadence radio survey. It's just that they have been. And the reason is because if you want sensitivity, and decent angular resolution, you need an interferometer. And so say the VLA, and the field of view is tiny. So the time it takes to map the whole sky is very long. So the VLA sky survey, which is our current kind of state-of-the-art radio survey, I think the cadence is 32 months. And they're also doing other things because it's a facility that does a lot of follow-up. So they don't spend all their time doing the sky survey also. So that's not as fast as it could go, but that's the cadence. I mean, it's not a huge, because radio emission tends to be slower anyway. So it's not crazy. It's just that you're not going to do an early discovery with that. DSA 2000 uses a very different approach. It has a huge number of dishes, very closely packed, and their cadence is going to be about, I think the last that I saw was 4 months. So that's much faster, but it's not what we're used to from GRB, and this is fast. And that's the fastest one that I know of, at least in terms of an all sky survey, which is how you discover rare transients, you need wide coverage. Yes.
If this is something you've been thinking about, could you say a few words about Einstein probe and whether you see that significantly contributing to what you've been trying to figure out?
Oh yeah, absolutely. Yes, absolutely. So for those who don't know about these surveys, decades ago, actually, we had X-ray missions, HEDI-2, BEPOSAX. They discovered all kinds of interesting things, these X-ray flashes, and there were all these papers of, are these GRBs, or these dirty fire, what are these things? But we didn't really have follow-up capabilities at the time, and so it just was not clear what these things were. Then they ended, and then it's been decades, we've had no X-ray mission. And now as of last year, we have suddenly this proliferation of X-ray missions again. Einstein probe is one of the most powerful ones, but there are trade-offs. So Einstein probe can see a huge area, 3,600 square degrees, so almost 10% of the sky. And it has a very high time resolution, soft energy, sensitivity. The problem is that it has a very narrow energy band, and so you can't say anything about the spectrum of the gamma rays that you're seeing. So that's a bit of a problem. And then there's SVOM, so Space Variables Objects Monitor, launched the same year, different, so a very wide energy band. So you can actually tell, is this a X-ray flash? Is this a GRB? What is this? But they have a smaller field of view. So they're complementary, but yeah, I think they will help in a number of ways. One is that some of the things I just described, I've given kind of an optical perspective, and I think at this point we've learned the limitations of the optical discovery approach, but they will sort of overcome some of those limitations. So for the dirty fireballs, you can actually see the properties of the prompt emission, or if there's no prompt emission. For the choked jets, similarly, you'd expect these things. I don't have it here anymore, but GRB 060218 was a sort of X-ray burst, and we haven't seen very many things like that because we haven't had the right kinds of surveys. But these are much better suited, especially Einstein probe, much better suited to finding things like that. Another subtle thing is that Einstein probe dwells for longer, so it stares for 20 minutes or 20 minutes. I think it's 20 minutes before it moves. And 060218 was a very slow burst, it was 1,000 seconds long, not the few seconds of traditional GRBs. And one problem is that our current GRB monitors, so Fermi, for example, it cannot find very long GRBs because it has to identify them above the evolution of the background. But the time scale of the background evolution is very similar than to these really long duration bursts. So you'd also find more low luminosity GRBs, which we have only a handful of really well-studied examples. And maybe some of these make prompt X-ray bursts. We have no idea because we just haven't had the capabilities. So yes, I think it'll make a huge difference. Any other questions in the last 3 minutes? Yeah, Kishore.
So if you had a question that you should go ahead.
Okay.
Sure. So I had a question about, so if we expect the radio afterglow to persist pretty long, does that mean like a higher cadence radio survey like TSA 2000 would get like a pretty complete sample of like nearby?
Yeah. So I think that's really its strength. I think it's hard. It's very sensitive also. Much more, I mean, it's an order of magnitude. Wait, think for a second, 0.1. 2 orders of magnitude more sensitive than the VLA sky survey. The problem is that it's gonna be very hard to tell what's what from just these light curves. But the way I kind of think about it is as free follow-up in a much more unbiased way than what we're able to do right now. So you could imagine if you could follow up all the 1C broadline supernovae, we would have much better statistics on what fraction could have jets or not, but no one has really been able to do that because it's a very expensive project. So I think in conjunction with other surveys, it's very powerful for that, yeah.
Yeah, I was gonna ask if there would be any utility in like getting like the pre-coverage from like a really sensitive optical survey like LSST. Like, would you expect to be able to detect like the 1C like curve for like more of these then, or like other?
Yeah. So I think okay. One issue is that this is the wrong hemisphere. This is a northern hemisphere project, but there's still a lot of overlap, but it's not perfectly well suited. So yeah, I think you'll definitely it'll be nice to see the combination of LSST, optical transients, and DSA 2000 radio counterparts. That would be a great project. Yeah. But yes, I'll just leave it at that. Maybe, 1.5 minutes. Yes.
Okay, so you were saying about supernova 2006 AJ that had a GRB.
Yeah.
I have read about that supernova and read about an X-ray flash you were saying, and a few years ago, those events are thought to be like maybe similar but with different luminosities. X-ray flashes being less luminous than GRBs. But I don't know nowadays if these are 2 different events or maybe just the same event, because with actually aims to improve mission, maybe I think there are more fast X-ray transients that has higher luminosity. So I don't know if these differences.
Yes. So I think is the question, what's the difference between a low luminosity GRB and an X-ray flash? Yeah. So these can overlap. Luminosity, I think these are observational words-based names. So luminosity GRB just means that the isotropic equivalent luminosity is less than about 10 to the 48 ergs per second, which could be kind of in any band. An X-ray flash means that the peak energy of the prompt spectrum is below, people use different definitions, but maybe below about 30 keV. So those things can overlap, but you can also have one without the other. So 98025, the GRB associated with supernova 1998 BW, the prompt emission was higher, so it's not an X-ray flash. But 060218, I think the very initial, so the spectrum actually evolved very quickly, and I think it might have reached higher energies as well. So I don't even know that that's an X-ray flash, but there are some true X-ray flashes like supernova 2008D. So from kind of shock breakout, you can get things that you'd really call an X-ray flash. Yeah.